It's a new day, it's the start of a new course, let's talk about some materials. Making materials is going to be a quite important thing for making your games, and in my Unreal Basics course I said at some point in the future I'm going to do a materials basics course, and this is the day. We're getting started today. I've got a lot to talk about, so let's right away get into the start here. First thing we do is we just go and make a new material right away. And I'll just call this for now a tutorial material, just to keep things simple. This introductory video is mostly going to be going over the most important basic things that we're going to be using and referencing a lot, and I need everybody to be on the same page about this. So first and foremost, we've got our material graph here. Here we're going to put in all of the nodes, and we're going to do like a lot of math and a lot of fancy stuff to make the material effects that we want. So if we, for instance, add in a vector 3 constant, which you can also do by just holding down the 3 key on your keyboard and clicking. Same thing with a vector with 2 values and a scalar value, which is just 1 value. You can even do it for a vector with 4 values. So that's how you make these constant values very easily. You're gonna see me like just spawn in a lot of these throughout the entirety of the course, so that is the first most important things. Now, once we have a value, this can be a texture or a constant or whatever you want, we can plug these inputs into any of these outputs. And I'm not going to talk about all of them because frankly a lot of them aren't going to be relevant until we actually talk about their specific relevance. But the most important ones are going to be the ones we talk about here. So first and foremost is the base color. And you can see as we update this, it's just the color of your material. Let's just keep that at pink for now because it's a nice color, or maybe let's go with a bluish color, bluish purple. That's a little bit more pleasant to look at. Then next up we have metallic. Metallic is usually a grayscale value, which is just to say it's from 0 to 1. Base color is something that you usually put an RGB value in, so something with 3 values. Metallic only uses a 0 to 1 scale. So if we put the metallic into here, you'll see nothing actually changes. Until I set this to 1, at which point it just becomes a little bit more metallic. There's a lot of technical explanation, which I'm going to be frank with you, I don't have the skill to explain to you what this does under the hood. But this is just a part of the PBR, which stands for physically based rendering pipeline, which a lot of modern engines use. And there's just a value for metallicness. That's just kind of everything you need to know. Usually this value is just straight up 0 or 1. You can put any value in between, like this being semi-metallic. That is a possibility. I don't end up using any values other than 0 or 1 all that often. So we're just going to stick with 0 for now. Then we've got specularity and roughness. I'm going to go for roughness first because roughness is the amount of reflectiveness that your material has, which again is just a scalar value, just a scale from 0 to 1. So the default value for that will be, I think, 0.5. If we plug it into this, you can see the roughness at 0 makes this very, very reflective and very shiny. But if I put the roughness up to 1, it is entirely non-reflective and almost looks like chalky, very diffused. The reason it's called roughness here is because this is how a rough surface deals with light. If you have a very smooth surface, like a mirror, that reflects. If you have a very rough surface in real life and you shine a light on it, it scatters the light all over the place and as such doesn't give good reflections. Now, why did I skip specularity? Because for the most part, you're just going to not touch that all that much. But specularity has to do with the highlights on reflections. Now we have a very like hotspot highlight here. If I just open this material editor as like a little bit of an overlay here, and we change the specularity to 0, you will see that it is a lot smoother in its fall, which is very closely related to reflectivity, but it's technically something slightly different. Again, if you're just going for reflectivity, you're going to play with your roughness. I could go into a very long, drawn-out explanation. Just remember that it is the intensity of the highlight spots in your reflections. and that for the most part, you're just gonna not touch it. And the same one for, I can never pronounce this one, but the one on the roughness, that's just to do with the specularity as well. Again, we're not gonna really touch that. The more important thing though is the emissive color. Now we get into the interesting shit, right? So if we disconnect the base color here and instead hook this up into the emissive color, initially you might think that this doesn't really do that much. It's a slightly lighter color, but that's about it, right? Well, this is where we get into some interesting shit. We'll talk a little bit more about like math and multiplication and stuff like that in the next video. But if we multiply any color value, an emissive color can go beyond a value of 1. Everything in a material is always on a scale from 0 to 1. Emissive colors can output things beyond a value of 1. So if we have our color here and we multiply that by like 5, you can see that it starts to have like this little bit of a glow around it. If we like make this 50, you can see it even more. The material itself becomes pure white because the color that it's trying to display on the surface is way beyond a value of 111, which is just pure white. But the color around it that it is now emitting is the color that we put in. And if you're using lumen, global illumination, this actually also does emit actual light into the world. So right here you can see we are not using lumen by the looks of it, because it's not emitting light into the world. If I now set my graphic settings a little bit higher to something like Epic, for instance, you will see that, hey, now we're suddenly emitting light from this thing. So that's just a graphic setting thing as well. So that's quite nice that you can emit light from materials. It's not particularly efficient for lighting, but it can be really, really nice. Now, if we use this multiplied value and instead of putting it into the emissive color, we put it into the base color, it will just be white. And that's about everything there is to it. So if we go here, it's just white. You'll also note that when you use emissive color, your metallicness and your roughness really don't matter because emissive color kind of overrides pretty much everything that's happening on the material itself because it's not interacting with light hitting it anymore. It itself is now emitting light. All of this stuff is just telling the material how to deal with light hitting it. And if the material itself is the thing emitting light, it's not actually dealing with how light interacts with it as well. So that's an important distinction to make. Let's go back to the base color here for the moment because I want to show you some other things as well. Next up we have the normals. If you don't know what a normal map is yet, it's kind of annoying to explain, but I will try my best. So a normal is the perpendicular angle of a face. So if we have a mesh like this right here, this face here is going in a up and down direction. It's actually exactly aligned to just the world Z direction, just the up direction, right? The normal of these faces will be pointing out perpendicular to that. So they will be pointing out into this direction in the X direction exactly. Now, that's the normal on a per face basis. That is the normal of your mesh itself. What a normal map can do in a material is, instead of calculating that on a per face basis, it can calculate it on a per pixel basis, meaning that you can pack in a lot more detail into your materials and your textures without actually having that detail present in your 3D mesh, which is a lot more intensive to render. Now, with things like nanites becoming more and more prevalent in workflows for games these days, you might think that you don't need that anymore, but still, it's really good to do, especially since you can generate this procedurally fairly easily in some cases. And we still have things like skeletal meshes that don't support nanites. If you don't want nanites on a mesh for other reasons, which we might get to in this course, you still have all the options for detail in your normal maps. That being said, if you get real close to the models that have these materials with the normal maps on them, you can see that there's no actual like depth there. It gets most of the way there with faking it. So what I'll do is I'll put in a texture sample real quick, and I think we just get some normal maps given to us. So normal maps will be looking a little bit like this. A very similar color actually to what our base color is that we chose. So I'll choose this default normal map for like, I think it's a tiling thing. And if we put that into the normal input here, we can see that we get some interaction with the light. It's casting shadows inside of itself, even though there's no geometry to support that. And I'm just going to change the color of this because I don't want you to confuse the normal map and the actual color that we have. So if I real quick go into modeling mode here and I add a extra little block here that I can put a material on, something like this, and I put our material on that. And just to make things easier to see, I'm going to make the roughness set back to 1. And now you can see there's a little bit of like texture detail in here, even though there's no actual mesh to support any of that. And the nice thing is, this is not just like an image that is projected onto this mesh. This will actually actively interact with light as well. So it might be kind of hard to see, but if I move across this with the light like this, you can see that there's a little bit of like updating of shadows. Specifically, look down here, not so much on the line up here, but the lines down there. As the light moves around it, you can see that it's casting shadows in slightly different ways onto its own texture. So that is what a normal map can do for you. Now, then we have tangents, which ties back into the whole specular thing mostly, so we're not going to be talking about that, because again, it's a nightmare to really work with, and you're not going to do it that much. World position offset, though, is an interesting one, because this can be a, like just a value going from 0 to 1, as always, or more, actually. And this will offset vertices, so points in your 3D mesh, in 3D space based on a texture. So if I use a texture sample here again, and I will put in a noise texture, which is just something that the starter content offers you, and putting that into the world position offset. If your mesh is high detail enough, this will now start distorting the mesh vertices all over the place. So I'll subdivide this mesh a good few times until we have like a very smooth mesh, and I'll just do that in a linear way. Checking this on wireframe now, we've got a whole bunch of detail packed into this. And for now I'm just going to add this vertex world space normal, and we're going to multiply that with the texture sample, and we will multiply that with a just a value to make it a little bit more extreme, just to show you. Don't worry if you're not keeping up with this, but now you can see that there's some displacement of these vertices based on the texture input here. And it will do that for this mesh as well. This is, however, limited to the mesh resolution. So if you have a very low resolution mesh, this is not going to work too well. And if you are wondering what this is doing, if you don't get this, don't worry about it. We'll get to it at some point in the future. This is taking the vertex normal, so every single point in your mesh has a normal. Again, the direction just pointing outward from it. And then it's multiplying that normal by a grayscale value here. So that is the amount that specific vertex is going to get displaced. And then I just multiply that with a general number that makes the effect just greater all over. And the last important one that we have to cover is the ambient occlusion, because when you're dealing with lighting situations, specifically for static meshes a lot of the time, there's this effect where if you have a little corner in a room, for instance, the places where lines come together tend to be a little bit darker than everything around it, just because of the way light bounces around. And generally speaking, that is kind of a pain to like simulate in a lighting engine. So the way they get around that is to have a ambient occlusion map. So this also is just a grayscale value. So that's 0 to 1, or again, a gray texture like this. But in this case, you really do need it to be a texture. You can't just do one number over the entire material because that kind of defeats the purpose. And in this, it's kind of difficult to show you what it does. So instead, I'm going to just put an image on screen right now that shows what ambient occlusion does. Now, then we have things like refraction, pixel depth offset, shading model, surface thickness, all that stuff we're not going to talk about. Refraction could be interesting. That's just literally how light refracts through a material. So if you're making things like water, that could potentially be interesting. But all those, you might notice, are grayed out, which is a little weird, because why is that? That is because we've got a couple of different blend modes and also surface domains. We can make like decals, we can make light functions, volume, post-processing, user interface materials, all with our own purposes. And then we have got a bunch of blend modes as well. So the most basic one and the easiest to render is just opaque, which means there's no transparency whatsoever. You're not going to be able to look through the mesh in any way, shape or form with an opaque material. But if we change this to instead being masked, you will notice that the opacity mask now becomes available. An opacity masked material will allow you to have an opaque material with holes in it. So you can't have something be halfway see-through with a masked material. There's some tricks that you can do to make it seem like that, but really all it can do is say, hey, these pixels are see-through and these pixels are not see-through. And that's why the opacity mask comes in. So again, I'm going to use this noise texture real quick for that, and I will actually disconnect the world position offset. And you can see now we can see through this at certain points in the material, which is really quite neat. If you look in the details here for the mask value, opacity clip mask value, this is the value where it decides, okay, so everything under this I'm going to be able to see through and everything over this is going to be opaque. So if I set this to 0, you can see that it's entirely solid. If I set this to 1, it's just going to be entirely invisible. The default is set to 1/3. You can set this to like half, so everything under 50% becomes see-through, and you can do some really, really cool stuff with this. Now, next up, instead of the masked mode, we have the translucent mode, which is just a little bit more interesting because it gets rid of quite a few things here. You can't make this metallic, you can't make this reflective because you're going to be able to see through it instead. It can still be emissive, but it doesn't have a normal input either, and instead of an opacity mask, it just has a opacity. And this opacity allows you to just have any amount of see-throughness between 0 and 1. So there's a lot more freedom that you have with your opacity in this, but this also takes quite a bit more rendering power to do. Specifically, if you have a see-through material behind another see-through material, that then creates some overdraw, as it's called, and that adds up really, really, really quickly in how difficult it is to render certain pixels. So generally speaking, this is a really powerful thing to be able to do, but also something that you should probably try to avoid using whenever you can. And those are the most important blending modes. We've got a couple more like additive, which is very similar. Additive is mostly used for things like materials, for particles and that kind of stuff. It just blends a little bit differently with what is on its background. And that gets into some like more in-depth, some more advanced, like how blending modes work to begin with. If you've ever worked with like Photoshop, you're familiar with blending modes, and you probably know what an additive blending mode does. If you haven't worked with anything like that, this is not the video to explain it in depth for you. And everything under that, we don't really want to talk about today. So those are the blending modes. Again, we've got some material domains, which we can talk about in the future maybe, and then some shading models, the most important ones being the default lit, which is just this, and then we've got unlit as well, which disables quite a lot of the pins here. So if you've got a material that only needs to emit color, it doesn't actually need to calculate any lighting information about itself. It only needs to emit colors. Or a material that just needs to be like entirely black, like you see here, that doesn't interact with light whatsoever. You set that to unlit, and that just saves a little bit of calculation power because it's not calculating stuff that you don't need it to do anyway. And then there's some more stuff that we can talk about later here, like subsurface can do some interesting stuff. Hair and cloth materials are kind of fun, but we don't really care about that for the time being, so we're going to set it back to default lit. The last thing I want to talk about for right now is having a two-sided material. If we come down into the preview settings here, we have a couple different meshes that we can preview things on. And I'm going to look at the plane for now, because as you can see, one of these sides is opaque, and the other side is entirely see-through. And that is because only the front-facing direction of any specific part of your mesh is going to render by default. Because think about it, if you have your character, it renders the entire mesh on the outside. There's no reason to render the mesh on the inside as well, right? Because you're never going to look in there, and why would you spend resources and computing power to render that? Sometimes though, you have things which you need to be able to look at from both sides. A good example of that would be like a blade of grass. Instead of modeling an entire blade of grass in 3 dimensions, you can make it flat planes and instead make those two-sided. That way they just render on both sides and you don't need to model any depth to them, and then that actually becomes more performance. There's a bunch of things that you can use this for, but don't use it as a crutch for things just not looking correct, because you're probably earlier on in your modeling process something went wrong if this is just a crutch to make things look better. Do be aware why and when you use this one. So that's just a whole bunch of information dumping on materials that you just need to get up to speed with. We need to be on the same page on what everything here means before we can move into talking about actually making the materials. So this has been a very information dense video. Moving forward, the videos are going to be hopefully a little bit less long and hopefully a little bit more actionable in their information. We've made it through the basics of how materials are made and how they're set up, and now today let's talk about a lot of math, because while we're making art here, we're making visual stuff, there's quite a lot of math involved, because at the end of the day, we're communicating with a computer, and those speak in the language of math. So no way around it, let's get started. I'm going to be making a separate new material. You can see I've imported 2 textures here. This wasn't entirely necessary to be a texture, but I like showing it off with a texture, what I'm about to do. So we're going to be talking about UVs and about colors today, which is what I made these 2 textures for, to show it off. So let's get started with a material here, and we'll call this UV math, something like that, and open up that material editor. So first things first, I'm going to just import this texture here, and we're going to set that to being the base color. And I'll show you this in the plane view, because this just displays our texture as easily as that. And this is where we get into some important stuff. Because if you don't know what UVs are, the UVs are your 3D mesh cut open and splayed out into a 2D space. So if you've ever, when you were a kid, done like papercraft projects where you print out a thing on a piece of paper, then cut it up and then glue it all together, and then you have like this little 3D thing. UV unwrapping is the opposite of that. It is making the 2D cutout version that makes the eventual 3D model. Except for digital 3D models, usually it's a lot more complex than the paper crafts that we give to children. And UVs are not measured in pixels. The actual textures that you put in them are of course measured in pixels. The resolution of the texture that I have here is 1024 by 1024. But the UV space itself, if I want to pick a place inside this, doesn't actually like work with pixels. It works on a scale from 0 to 1. So it's much more of a simple coordinate system that can infinitely scale up and doesn't really have a resolution. Again, the textures that you put inside of it will have, of course, a resolution, because that's how images work. Why am I explaining all this before we get started with any of the math related stuff? Because you need to understand how these things work to begin with, because the math we're about to do here with the UVs is going to impact how this displays. Now, the UVs are just the X and Y coordinates of the UV space. So we have the U and the V, or the other way around. I can never remember. I always just mess it up first try. UVs are to me what USB keys are to most people. Like you try it once, it messes up, and you try it again, and it messes up again, and then you try the thing that you tried the first time, and magically it works. That's what UVs are to me. So we can do some math with these UVs. And if we just get our texture coordinates, which we can get if we just type in texture coordinates, what you can also do is just type coord, and that also gets you the same thing. Putting that into our UVs here literally does nothing, because this is giving us the untiled, just raw texture coordinates, which is 0 to 1x or u and 0 to 1 v or y, The reason I use UV is because this is a 3D like art workflow, and in 3D art we use XYZ for the spatial dimensions for the models themselves. So U and V have been dedicated to the 2D texture dimension space. And we can say we want to tile the textures in certain ways. And here you can see, okay, now it's squishing things together. And hey, we've got the lines that I had before. We've got like 5 of them now. And that makes sense because we're tiling the U 5 times. And we can tile the V 5 times. And now we've got 25 of this texture in total. It'll be easier to see if I just tile them both by 2. So now I've got 0, 0.5, 1, 0, 0.5, 1. So it's the same texture, just repeating, tiling itself. The texture coordinate node can do that by itself. I think it'll give you a better understanding once we start talking about how to do this manually with math. Because if we split this up first and foremost, so we can break into 2 components. So this gets us a R and a G component, which is the same. R and G is the same as U and V, which is the same as X and Y. They're just names for things that we use. RG is for RGB. Those are usually used for colors. X, Y, Z are used for spatial location, and U and V are used for texture space. Since we're working with materials, whenever we like break a vector in a material graph, it uses the RGB naming, but it doesn't necessarily mean that these are like color channels or anything. Let's combine them back again with append. So we can append vector, and that lets us put 2 singular values, so 2 scalar values, 2 float values, whatever you want to call them, back together into a singular vector 2, which is what a UV is. Why did I do that? Because it doesn't accomplish anything. Well, now I can independently do math on the U and the V channels. So if I say, hey, I want to add something to this, I can say, hey, I want to add to the U channel. And it doesn't necessarily do anything, because right now what we're doing actually is we're taking 0 and we're adding 1 to it. So that becomes 1. So the entire texture gets displaced 1 entire tiling over and ends up looking the same. But you can see if I add 0.5 to it, now 0.5 will be at the left hand side. Then it adds to 1 and 0 and then goes back to 0.5 where it ends again. So this is just displacing the texture a little bit to the left. And if I do like 0.25, it displaces it a little bit less to the left, and so on and so forth. So that is how we can move textures along. So if you want to make a texture that scrolls, all you need to do is add to the UVs, either the U or the V or both, and multiply that by a time. So we can actually quite easily just do that by using the time node, which we'll use more in the future. But if we just put the time node into this addition, you can see it's now scrolling this texture over and over and over again, which this texture tiles fairly well, so that's why it's relatively seamless, because it's adding to the UV space. Now, of course, if we want to add something, we can also subtract things, which will just move it in the opposite direction. It really is just as easy as that sometimes. So if we do this, it just moves it in the opposite direction. So adding and subtracting are just for scrolling your texture over your mesh. But adding and subtracting aren't the only things we can do. We can also multiply and divide. And this is where the stuff actually gets really interesting, because that is what tiling does. If we multiply this just by 1, nothing happens because everything stays the same. But let's just, before I actually do it, let's just think for a moment here. If we multiply 0 by 2, it stays at a value of 0. But if we multiply 0.5 by 2, it becomes a value of 1. If we multiply 1 by 2, it becomes a value of 2. So what do you think will happen when we multiply this channel by 2? The answer is that it starts tiling. And why does it start tiling? Because it's not the values that we see on this texture that get multiplied. Those are just pixels in a texture. That's just for visual explanation for this video. What's actually happening is it's expanding the UV space itself. So what this is really doing is this is still 0, this is 0.5, this is 1, but then this is just 1.5, and this becomes 2. And if we, again, multiply this by like 5, it tells it even more. So this is 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 5. So that is how we can tile these textures with multiplication. With that understood, I guess you can understand what is going to happen when we divide this by 2, because division is just doing the opposite of what multiplication does. So this instead will zoom things in. So our coordinate 0 stays the same because multiplying or dividing, well, dividing by 0 is not possible, but multiplying or dividing with like 0, that is a fixed point. But then when we get to this is now the end of our texture space is 0.5. So our texture stops at where I marked 0.5. If we go back real quick to my multiplication here, with multiplying by 5, maybe that will make it a little bit easier to understand, because now we've got the whole 0.5, 1, 1.5, etc., up to 5. If we then divide this by 2 again, it will zoom in our texture space in the U direction, 2 being at 2.5. And so it does. We've got 0, a half, 1, 1.5, 2, 2.5. So that is the basics of how we can manipulate UVs with multiplication and division. Those are very important. And then addition and subtraction. Frankly, subtraction is kind of a moot point, because generally the way I end up doing it, if I want to subtract something, I just add a negative value. Just makes more sense to me, but you can just subtract as well. Sometimes it is easier to subtract than make something a negative value and add it. The multiplication and division to a certain extent also have the same thing, of course, because they just accomplish the same thing in opposite directions. But for these, it can be very nice if you want to have like a parameter that you can use to, and we'll talk about parameters a little bit later on, to zoom in on a texture, you want to divide that, and if you want to zoom out on a texture with a parameter, you do it through multiplication. Now, all of that out of the way, we're going to delete this stuff again, because we've explained UVs and we've explained how to multiply and add to them. Let's talk about the same thing, but for color instead. So I'm going to switch this texture over to being my gradient texture, which, by the way, the reason I say I didn't really need this texture is because Unreal just has a linear gradient node as well, which kind of does the same thing. It has a U gradient going from left to right and a V gradient going from the top to the bottom. I made this one myself just because I think it'll demonstrate my point a little bit better. And I actually do want to go back to the texture coordinate real quick, which I just had. Just because what I want to do is I want to show you the whole like tiling and moving thing with a texture that doesn't tile as well. So what we'll do is we'll take the V channel here and then start moving that up and down and scroll that with the time node. And now you can definitely see like it's actually the texture scrolling around. It's got a very obvious cutoff point here because it's of course a gradient. So I just wanted to show you that real quick to end that off. Now, we don't need any of this anymore. We've just got this gradient texture and we're going to talk about the addition, subtraction, division and multiplication for color stuff, because this becomes very, very interesting very, very quickly. First things first, let's do the simple ones, addition and subtraction. If we add nothing to this, what ends up happening is nothing. If we add a half, what ends up happening is everything just becomes a little bit lighter, because the colors as well work on a scale from 0 to 1. So if we have at the very bottom here a value of 0, and we add 0.5 to the entire thing, we now don't have a gradient from 0 to 1, we actually have a gradient from 0.5 to 1.5. Except that the base color, as we talked about in the last video, can't actually display things above a value of 1. So really what we have is we have a gradient from 0.5 to 1 and then clipping all the way up to the top. And in much the same way, we have the subtraction node, of course, for which we can say we want to subtract 0.5, in which case we will have a gradient that is minus 0.5 to 0.5, with the actual 0 point being in the middle here. But much like it can't display values over 1, you can't display a value darker than black, right? Just 0 is 0, and anything under 0 will just be displayed as 0. So what this does is it more or less just moves the line up. Now, with just these gradient textures, that doesn't necessarily make full sense to you, potentially. So I'm going to add a constant here. And what we'll do is we'll just make this like a nice little blue color, put that into the base color. And I'm going to, instead of doing this gradient texture, we're going to use the Berlin noise texture again that I used last time. And we're going to add this texture to that color, because this is where stuff gets real, right? If we add the texture here, it will do the operation for adding a value for every individual pixel. So we've just been adding like blanket values over the entire material so far. When we do this with textures, it's going to take every single pixel and do that addition operation based on the texture that we're putting in. So if we do this, our base color will be that blue, but it will then get a value added to it depending on the noise texture that we're putting in, making a very like blue kind of texture, which this can be really, really nice to work with. We actually don't have any pure blacks in here, because everywhere that's pure black in our texture is just going to have nothing added to it at all, and as such is just going to be the base color blue that we have here. And everything then going up toward a value of white is getting more and more and more added to it, and as a result will tend toward white, and that's making this nice little like marble-ish blue color in this case. And of course we can do the very same thing with subtraction, which means that everything that is very white in this texture becomes very black, and everything that is very black in this texture remains to be blue. I don't think this is as pleasant. Do you? I don't think so. That leaves multiplication and division, which are the most important ones, I would argue. Specifically multiplication, because multiplication can be used as a mask. And what do I mean by that? Well, if we take this just directly into the base color, it's just this blue color. And if we add something to that, we can make that like nice marble-ish blue color that we had before. But if we, instead of doing that, do a multiplication, again, it's going to take each pixel from this texture and multiply it with the value of this blue. Meaning that everywhere that's going to be a black pixel in our texture is going to multiply our blue value by 0, or a value very close to 0, and make it a darker value. Everywhere this texture is white is going to multiply it by 1, and that means just keep this the same way it is in the input. That's the way we can mask things out, with multiplying them, and that ends up with this. It's a little bit easier to understand and work with if we actually make this a translucent material instead and put this into the opacity, because that's what you use masks for all of the time, like opacity related stuff. And for that you actually do want this to just straight up be white instead of being blue. But now we can see, if we make another node here, put that into the base color and make this a blue color again, we have a opacity mask because we multiplied our texture here by just a value of white, which needs to be pure white. And that's how we can multiply things together. So we can also do this for base color, of course, if we have that texture that we had before. So let's just copy this over real quick and use that gradient texture that we had a moment ago. If we multiply these two things together for the base color, and we'll just keep the opacity at full and set this back to being opaque because we're not using the opacity anymore. Now you can see it's not just taking like a mask from one to the other. What it's doing is it's multiplying these two together, right? So anywhere there is a dark pixel on either of these is going to be a dark pixel in the output. And anywhere there's going to be a light pixel in both of them only is where it outputs light pixels. So we've got the normal noise texture that we have here, combined with a gradient here that is using it for multiplication. And of course we can combine it with the textual coordinate stuff that we just learned. And there's another important lesson, is you can actually multiply like vector 2s and vector 3s with just scalar parameters. And the output will be a vector 2 or a vector 3. like I showed you in the previous video, when I multiply the color by a single value, that just multiplies the color as a whole. And you can do the same with these texture coordinates. So we can multiply this, even though it's got a U and a V, so it's got two components to it, we can just multiply it with a singular value and it will just multiply both of those components. So let's say we multiply this by 5 and put it into the UVs. Now that noise texture is a little bit more tiled, and we can do some neat stuff with this. Now, that only leaves division, and I'm going to be real with you, division doesn't strike me as the most useful thing to do for color operations. I'm going to show you what it does anyway, but you don't really care. At least I don't really care usually. So let's divide. And of course, with division, it becomes important which one you divide by what. Multiplication, it's kind of indiscriminate, but for division, that suddenly becomes relevant. And here you can see how division works. So what we have here is this gradient. We are dividing by 1, which is just the same value that you put in. And we are slowly going toward dividing by 0, because black is a value of 0. And dividing by 0 gives a value of infinite. So this gradient is going from, hey, just show your normal color, to be brighter and brighter and brighter and brighter toward infinity. Of course, we know that it gets clamped at a value of 1, because normal materials can't display anything above a value of 1. But now if we switch these two around, what you'll see is it will give you a very different effect. And this is actually kind of like a neat effect, right? I like how this looks. Because what it's doing right here is it's taking this and doing the division stuff with the bottom texture. So we get different effects depending on how around we do this. We can actually put this into the emissive color to show you that it really does actually generate values much above a value of 1, because you can see some glowiness here. I'm going to add a little fun thing to this, because this is at this point just a grayscale map, right? There's nothing much to this. But if we take this, which effectively is just a scalar value, we can multiply this with a color. Let's say we multiply it by like a red color, and then we'll have the exact same pattern. It's more of a peach actually, but we'll have the exact same pattern but in that color now, which is really, really quite cool. And especially here you can start seeing that, hey, we do have some like burnt out areas, even though we don't have any white color going directly into the outputs. So once again, that's quite a lot of information about math and UVs and colors and all that stuff. It's just some stuff that you have to go through. If you're following like a full course on materials, feel free to refer back to this video at some point in the future if you get confused at any point. Specifically the multiplication and division for the UVs, zooming in and zooming out on your texture, can be really, really counterintuitive until you get used to it. And frankly, I also mess it up sometimes because it is counterintuitive. So pretty soon, with all of this theory out of the way, we can get started on actually making some cool materials. We've talked about some basic interface stuff. We've talked a lot about math last time. I'm very sorry I had to bother you with that. Today we're going to talk about math, but in a less headache-inducing way. We're going to be talking about lerping, about clamping, which also includes saturating, and then I'm going to throw in the if node as well as just a little bit of a fun bonus. So let's get started with the clamping node, because I think clamping is the most easy to understand. So if we just take our noise texture that we have here, and I'm going to just tile this a little bit less so we have some more rough details in here. I'm going to run that through a clamp node, and I'm going to remove this as well. And by default, the clamp node will just say minimum 0, maximum 1. And that is generally what you want to do. And the reason that we have the saturate node is this is literally just what the saturate node does. So if I put in a saturate node, that is just a simplified version of saying, hey, I want to clamp between 0 and 1. So you'll note if I put this into here and put that into the base color, literally nothing changes because that does the exact same operation. But what does clamping do to begin with, you might be asking still. We've got a couple of clamping modes here as well, but we're not going to worry about that for the time being. Clamping takes in a value, whether it be a single value or an entire texture, and it kind of just says, hey, Any value under the minimum, I'm going to bump that up to the minimum. Any value over the maximum, I'm going to bump that up to the maximum. So it will actually be easier to showcase if I put this into the emissive color instead. So we have this value. If we just put that into the emissive color, it does the exact same thing. Now, if I say, actually, I want to multiply this by 50, something like that, right? And put that into the emissive color, we'll have a very glowy little square because we're multiplying by 50. So every pixel in this texture that has a value of 1 now suddenly has a value of 50. If we run that through the clamping node though, that's going to say no, everything above a value of 1 is just going to be 1. So the color itself is going to be a very washed out white. Because everything that is lower than 1 is still getting multiplied by 50 and now probably exceeding a value of 1. Then we get to the clamping node and it's saying, hey, everything that's over a value of 1, we're going to get you right down the way back to a value of 1. So we can set this to a value of 5 instead, and now everything will have a maximum value of 5. But there is some loss of detail there, as you can clearly see, because it's not proportionally like pulling them down, it's just saying a cutoff. Everything above this value is now just getting immediately set to that value. And we can do the same thing with the minimum. So let's just say, hey, we want the minimum value here to be 0.5. Now everything that's going to be 0.5 or below is going to get pulled up to being a value of 0.5. So all of the blacks are now going to turn into the same gray color, which is actually probably going to be easier to see if we like divide this by something. So divide this by like 1.5 or something like that. And that then creates a texture where we only have a couple of little spots of light that are above the value that we're clamping from. So the clamping node itself has a little bit more freedom to it. If you just simply want to clamp between 0 and 1, which is something that you very often want to do in making materials, as we get into actually creating some of the materials, we'll see this some more in action. You can just use the saturate node instead. You don't need to add an entire clamping node for that. So that's how clamping works. Very important to understand, not all that flashy. So let's do something else fun instead. Let's do some lerping. And you might be saying, lerping, that sounds like LARPing. Do I need to get my foam swords out? And I'm saying, no, that's not what we're doing at all. I mean, if you want to get your swords out, you can, but I'm not asking you to. It's linear interpolation is what is happening. So a linear interpolation will take in an A value and a B value and a alpha value. So let's take two colors. So we're going to make this like two very contrasting colors, so something like red and blue. And if we put that into the lerp, we have an output that will be in between red and blue. So this should be like a grayish purple kind of. It's not even all that gray, to be honest with you. And if I put the alpha at 0.1 now, it's going to be closer to the input color for the A pin. And if I put this on like 0.8, it's going to be closer to the output color of the B pin. Now, that doesn't seem all too useful together, because if I wanted that color, just put that color in. But here we go again. If we don't just use one value for the entire material, but instead use a texture, it's going to do this lerping on a per pixel basis. So now we suddenly have our noise texture, but instead of just being black and white, it's now the same noise texture, but moving from red to blue, which can be quite cool to work with. I'm going to delete the tiling for now. And of course, we can do a lot of stuff with this. If they're a little less contrasting, that makes for quite nice potential textures like this. And of course, we can do a lot of like interesting math and multiplication and maybe like some distortion, maybe adding some other textures before it gets to this lerp. Right now we're just doing this with colors, but we can do this with entire textures, you have to realize. So if we just lerp between two texture samples, this is probably not going to look that good, I'm going to warn you, but let's take this wood texture, and then the other one, we probably have like a stone texture, something like that, right? Sandstone, you know, that works. We can put those in there. And these are just full textures with like a lot of detail in them. And if we lerp between these two, we now get this very weird looking in between of the two. And if we take this noise pattern, which we've been using, and we can use a node called cheap contrast, which just adds some contrast to whatever you put into it. We can put in a scalar value there. And usually you want to stick pretty low with the values for these. So let's do 0.15. Maybe we can go a little higher here, like 0.5. You can see the bottom texture coming through a lot more now. So if you want to make something like a texture where we have a wooden table with sand on top of it, this is kind of like a way we could start doing something like that. Of course, you would also then want to like displace the places where there's sand, and you want to have a different normal map for those places, but that's just like more complex setup here. But the basic idea is you're looping between two different textures. You'd also just be looping with the same input alpha between two different normal maps. Which, you know, let's just try to see if we can find the corresponding normal maps to these, because I imagine that can't be that difficult. Let's also just copy the loop node itself over as well. And you can probably start seeing how materials end up becoming very big graphs very quickly if we're doing all sorts of this stuff. So this is going to look real weird because it's of course not using the actual normal maps, but if we have the texture for the, I think this is walnut wood normals, so we can use that one, and then for this one I assume that this is the normals for that. Which is a little bit weird because I was expecting this to be sand, but now it's also looping between the normal maps for both of these textures, making this very weird and fun effect. And either in the next video or a video sometime soon down the line, I'm going to be talking about vertex colors, meaning that you can set up a material where you can, in your viewport, paint between these different texture sets for your specific objects, which is a really, really powerful tool. It's a little bit beyond what we're doing here today, though, because we've had a lot of information-dense videos before in this series. Like the first two parts are very information-dense. Let's just keep it a little bit more light-hearted here. Looping, though, is something that you're going to want to remember. You're going to be doing this a lot, and it's honestly maybe the most important node that you're going to be working with in materials. Now that we've talked about clamping and looping, I want to talk about one last thing to end off this slightly more simple video, and that is I want to use the if node. If you're into programming, you'll know what an if statement is, probably. We can do something very similar with materials. So let's put this into the base color, and here we put in a value and a B value. So we can say, for instance, let's say we just take our noise texture as the A value, and then the B value we can just put as a scalar value. And we can, let's say, put this at 0.5. So now we put in some pins here saying, okay, what should we output if A is bigger than B? I'm going to say we output this red color. And if A is equal to B, so anywhere that there's exactly a pixel that is at 50% brightness, we're going to be outputting this pink color instead. And if A is less than B, so any darker pixels, what we're going to do is we're going to output like this cyan color. Why not? And once we hook that up, we'll get rid of this compile error, and we'll see now we have this noise texture where everything that is greater than a value of 0.5 is now just marked as being this orange color. Everything that is less than that is marked as this cyan color. But if we zoom in really, really tightly, what we'll be able to see is that there's a tiny bit, I don't know how well this is going to come through on YouTube, to be honest with you, but there's this tiny little line of where the pixels are actually the in-between color that we specified there. So that's this color. So that's the if node. Generally speaking, this is not a node that is used all that much. And we've also got a absolute insane amount of different math functions here, like flooring or ceiling, which is rounding up or down. We've got something for normalization, all that kind of stuff. We're not going to talk about all that too much, but I wanted to show you the fun little thing you can do with the if node. Again, the most important thing about this video is starting with the clamping and saturation nodes, and then also understanding looping. Looping is the one thing I really, really need you to remember going forward. We've been making a lot of material stuff. Let's talk about material instances and parameters, because Do you really want to make a whole separate material for every object in your game? Well, to a certain extent you have to, but there's also some optimization to be done there. So what we have is we've got our tutorial material, and then we've got this weird as just keyboard mesh material, and today we're going to add a third material to that. But from that we're going to be able to make a bunch of different materials. So let's just call this like flat color, and if we open that up, we get our usual material graph. So we're going to add a color node here to the base color, and we're going to set the color to like pink or something very vibrant. Now, if we want to make a second material here that is, for instance, blue instead, you might think, okay, let me just like copy this over with Control D and say flat color blue, and then going in and changing this to blue. But now these are two separate materials, which I'm not going to bore you with too much of the technical mumbo jumbo, but it is not particularly efficient to render separate materials when you don't have to. So what we can do instead is not make this flat color blue material, because that's a very, very bad idea. We can right click this color node here, and we can convert it to a parameter, which works the same way as you are maybe used to in programming. A parameter in a function or an event is just a bit of data that you can pass in whenever a function is called. And the same thing here. Whenever we make a material that is referencing this as its source, which I'll explain to you in a moment, don't you worry about that, it will give us just a little bit of a field in which we can input the color that we want that specific instance of it to be. So we can call this color, and this will now be the default value that this color has. With that, we can right click this flat color, and we can create a material instance instead, which seems like it will just be a material, but let's call this flat color blue. And if we open this up, we don't get a material graph. Instead, we get this preview here, and on the right hand side we get our global vector parameter values. You can give these values categories to make them a little bit more organized, but if we say, hey, we want to enable this one, we can just change this, and now we have this material but with a blue value instead. A material instance is a lot more efficient to render than separate materials, because more or less what happens is the engine renders your scene one material at a time, and there is a little bit of time in like wrapping up the rendering of one material and starting up the rendering of the next material. And these material instances are counted as the parent material. So if we have 50 instances of this material, those will all be getting rendered at the same time before we move on to the next parent material with all of the instances that includes. That's a bit of an oversimplification of how it works, but in general, that is the way you can look at it. So most games will have one big master material, because most objects won't actually require that much more work than just, hey, these are the texture maps that you're going to be using, go ahead and just render this as one material. So let's do one of those real quick. We can just say this is like material master material, and for those we can add in a texture sample node, and that will be our base color, for instance. Let's set a default value for that just to gray. And if we right click this, we can convert this to a parameter as well. So we can call this the base color, or the albedo map as it's also known. And then add another texture sample, and we'll just add in a couple of texture samples here because we're going to be using a few. Going into the metallic, and one into the roughness, and one into the emissive color, and then one into the normal, and so on and so forth. Now, one little note here is we are using a separate parameter now for metallic, for roughness, and if you wanted to use it, the ambient occlusion as well. You can actually combine those into one texture map to save a little bit of video memory, because we'll talk about that a little bit later on in this video. But for now, what we're going to do is we're just going to convert this to a parameter, and this will be the metallic parameter. This will be the roughness parameter. We have an emissive parameter now, and we'll also then make ourselves the normal map parameter. Give all of these a default value as well. For the metallicness, we want that to be black. For the roughness, we probably want that to be gray by default as well. Emissive, of course, we want to be black. And Unreal Engine comes with these very lightweight textures that you can use, like black and gray, just as default values. These are literally only a couple of pixels big, so they're really lightweight. If you don't supply any alternative like texture maps for them, they're going to be very efficient on your material. And then the normal map, I believe it also has a empty base flattened normal map. Just if we open that up, you can see the size is 1 by 1 pixel. It's just 1 pixel, but you need to give it a value in order for the shader to actually work. And the same thing here with the black. This one is 32 by 32. Still a very lightweight texture, right? So now we have our master material, and we can create a material instance for like our material instance, like our hero character or something like that, right? And in that we can supply all of the color maps that we have from like Substance Painter or from Blender or whatever we use to make our 3D art. And now most of the characters in our game can use the material instances from that parent material, meaning again, it's going to be efficient to render. Now, we talked a little bit a moment ago about the fact that the metallic and the roughness map and stuff like that, those are all grayscale maps, right? The base color, of course, has red, green, and blue values because we want to be able to mix colors and like have like yellow in there as well, like brown and whatever color we want. We don't need that for the metallic and roughness and ambient occlusion and a couple of other things as well, because those are just simply like 0 to 1 values that you input. So you don't actually need to use a unique texture for those. You can combine those into one texture. You see, if you have a, for instance, Berlin noise texture, right? This texture, even though it is only black and white, it stores information on red, green, and blue channels to create that white. Which is redundant, because those red, green, and blue channels are all going to be the same because the output is going to be in grayscale. So what we can do instead is, if you use something like Substance Painter and you're like baking your material maps in there, it has a preset for this for Unreal, I believe, which automatically does this. If you're doing this in Blender, maybe you need to do a little bit of compositing, import things into Photoshop and combine them. But let me pull up my own project and show you a packed map. So here we are in my own game project. Don't mind the absolute mess that the root folder is here, but we have a texture map here that is a joint material occlusion roughness metallic, as it is called. So if I open that up and show you, you can see this looks like an absolute mess of a texture. And that is because it's got the RGB all overlapping each other. But if I now import this into a material real quick to show you, we can put this into the base color and it looks like the mess that we just saw. But now if I only pull out the red channel from this texture, it's only going to be showing me the red channel. And that's then suddenly a grayscale value again. And if we look at the order of the name here, it uses occlusion, roughness, metallic. So red will be the occlusion, ambient occlusion. And then green, if we look at that, that would be the roughness. So this is the roughness map. So we can put that into there. Let's actually just put all of these in the right pins right away. And then we have blue, which is the metallic map. And this is everything how metallic it should be. So this can go into the metallicness. And now let's just give this a like 60% gray value or something like that. And this is now what our material map looks like when it's all properly hooked up. We have these 3 different things all stored in one texture, meaning that it only needs to load in one image instead of 3 separate images. Meaning that we're only using 1/3 the amount of memory in order to run this shader. And while we're in here, I might as well show you a little bit of material instancing as well. So this is the parent material for all of my enemies. The enemies have this thing where they can like fade away once they die. And all my enemies have this same material. So this is all of the like logic to run that material with like a Berlin noise texture sample and a lot of math and stuff like that. And if I then go into the material, turning off auto exposure here real quick so you guys can actually see, the material for one of my enemies I can click on this icon here and preview it on the actual mesh that I have at this point selected in my content browser. So this is the enemy itself. You can see I have a bunch of parameters here, stuff like the dissolve in. So if I decrease this, you can see that that material does that dissolving effect. I've got my base color for my lamp, I've got my emission map, and in this material I still have the metallic and the roughness in separate texture maps, because when I made this initially I was still doing stuff in Blender rather than in Substance Painter. I didn't really feel like every time exporting a model also combining those texture maps into one packed map, because I was lazy. Do as I say, not as I do. I still need to go back over this material and combine those and pack those together at some point. Now, one final fun thing is if we, for instance, go back to our flat color material here in our example project that I've been using, we can actually set these parameters on runtime as well. So if we go and make a quick blueprint here, just an actor, we'll call that PP color changer. I will add in a static mesh here. We'll just do a normal cube. And here in the construction script, what we'll do is we'll get the static mesh. We want to set the material on that static mesh. And we're going to set this to a dynamic material instance. So we can create a dynamic material instance, and that lets you select a parent material. This lets you select either a material or material instance. Generally, when you do this, you choose a parent material, like not an instance material. So let's use our flat color material here. We can give some optional values that we're not going to worry about right now. And then the output pin here is going to be a reference to the newly created material instance that we can change things about on runtime. So we can say set parameter, and here we can set a bunch of different stuff as far as parameters go. So we can set a vector parameter, we can set a texture parameter even. But for us, what we want to do is we want to set a vector parameter by value. So this puts in a linear color value, and the parameter name, this is very important. This needs to match exactly with what we called this. So this is color with a capital C. So we'll just say color, and then the value we're going to promote to a variable, and this will be the color. We'll just expose that so we can edit it in the viewport. And then after that, we're going to use the dynamic material instance that we just created to set that as the material for our cube. So now we can see that our cube will be black because that's the default value of our color. Now, we also probably, like, the alpha doesn't really do anything in this case. But if we set this to like pink, you can see immediately it shows up as pink. And we can do this in the viewport on a per instance basis now. Do be aware that these things are relatively intensive to run, because what you're effectively doing is for every single one of these objects, you're making a new material instance. And not just a material instance that has to keep parameters exposed to be able to be changed on runtime. Because you can also change these as the game plays. But now you can see we can set these values on a per case basis, even though they share the same parent material. So that's all really good, really powerful. You can do a lot of fun stuff with this. For instance, on begin play, we can do a timeline. And we need to do a couple of other things here. We need to promote this to a variable real quick. Material instance, just so that we can access it from the rest of the event graph. And let's just copy this over. I think that makes the most sense. We can loop this linear color between two different colors now. So let's say, hey, we want to loop this between like blue and maybe red, instead of using the color variable that we just made. You can of course make these two color variables and stuff like that. I'm sure you get the point there. In the timeline itself, let's make a flow track. Set the length to 5, that's fine. We add a key at 0, 0, and then we add a key at 5, 1. And that will then loop between these two colors. And we can use that timeline component that we have now to set looping to being true, just so that it loops. And now we'll see that as we play the game, it will go from blue to red, and then once it reaches the end of the timeline, it will loop around, so it will just reset back to blue. So this is how you can like animate a color like that. And of course you can get a lot more complex with this, with certain materials only being a part of a model, of course, those being the only thing that can change colors, and you can be very creative with this, right? This is pretty much the rundown on what both material instances can do for you with parameters, and also then using those parameters dynamically on runtime to do a lot of cool stuff with. Did you know that 3D models have vertices and edges and faces? You probably knew that. But those vertices don't just hold data on where they are in space. They also actually hold color data. And that's what we're going to be talking about today, because that's actually very, very usable. So if we go into wireframe mode here, you will remember we made this thing, which is like a very, very dense cube with a lot of vertices. All of these single points in space have some color data as well. So let's take a look at how we can use that. Let's make a new material, and I'm going to call this Vertex colors, because that is what we call those things. And we can just use the vertex color node. This is just a node that has a RGB output for the vertex colors and individual outputs for the RGB and A. It doesn't just have RGB, it also has an alpha value. So each individual point in space on your mesh actually has 4 values for you to use in your shader to do really anything you want with, right? We can just put this into the base color if we wanted to. And that way we can literally, if we make this material on this cube, for instance, we can start literally just painting those colors on. And the way we can do that is going into our modes here, and we can go into mesh painting mode. And if we go over to paint, we can set our paint color, and you will now see that I'll be able to paint in those colors on this material, because it is showing the vertex colors. If I swap around to material again, you will notice that this doesn't do all that much, because this material isn't set up to show the vertex colors. The one we just made is. Let's make the saturation a little bit higher on this though, so we can actually like properly see things. And I should also point out that this is not giving colors on a per pixel basis. This is giving colors on a per vertex basis. So if we have a lower poly model, like these walls, for instance, I don't think that these are particularly high poly count. If we make these that material and we go back into our mesh painting, you'll see now we have these 2 sets to this purple color, and it smoothly interpolates that to the color of the next vertex that it can find. So if we set these vertex or vertices somewhere over here, oh, it's all the way on the other side. For instance, to this red color, it now interpolates between those. The only things that we can actually give the color values to are the vertices themselves. So that is a limitation of vertex colors. They are colors for vertices, which means that they are limited in the resolution of your mesh. But this doesn't seem all that useful, right? This seems like, okay, why do I care about being able to paint colors like this? Why wouldn't I just do that in a texture? And the answer is, for this purpose, you definitely would do it in a texture. There is the upside of this having infinite resolution in like pixel space, because it's done based on the vertices. So even if I come really, really close by, you're not going to see like any banding. Well, you will, because you do probably. But if you do this in your own Unreal Engine, you're not going to see any banding or pixelation in the color here. This is going to be a very smooth gradient, which is potentially a upside. But again, this is not really something that you use for colors. Usually you use this for like more arbitrary data and things like looping between texture maps and stuff like that. Let's use it for that purpose instead. So what we'll do is we'll create 2 parameters here. And this will be color 1. And then this parameter will be color 2. And let's by default set color 1 to being blue, and color 2 to being yellow. If we then loop between these, and the alpha for that loop is going to be our red color channel, and that's going to go into the base color. We'll now see that suddenly everything is yellow except the things that have a little bit of red in them. But you will notice that we are trying to paint on and it doesn't do anything. And that is because this thing is already yellow. And if we go back into our material, yellow means a value of 1. So the entirety of this object already has vertex paints of 1, which is just like white across the board, applied to it. So there you want to use the erase color instead. So we just set that to black. And then what you can actually do is you can set it to only affect the red channel as we want right now, or the green channel, or the blue channel, or the alpha channel, or a combination of channels. And then holding shift and painting will apply the erase color. So now we can make this like little blue spot that we have here. And just like any painting, we can do like we can set the strength a little bit higher, so it's a little bit more aggressive, more fall off, or less fall off, so no fall off at all will make a very harsh line, which especially since this is vertex based, you probably don't want that. We have a size for the brush as well to really paint in like large areas at once. And we've got a number of different views here. So we have RGB view, which just shows you the vertex colors, the alpha channel, the red channel, and well, all the channels individually. We can see going through here. I personally just like usually painting in like just simply what the material outputs. And you can probably see how this would be useful, right? Because right now we're just to demonstrate this, like looping between two colors. But you can very much do this with two textures. So if we do that instead of doing two colors, we make two texture sample nodes. I'm not going to set these two parameters. You probably should in a realistic scenario, but we're not going to. The first one will be grassy ground, and then this, hopefully we have like dirt. There we go. That'll be good enough for this example. So now we can see that we have a Minecraft block, more or less. And going back into mesh painting mode, we can now say, hey, we want to have this be maybe a little bit smaller, grass over here. And then we want to have the sand over here. So we probably actually want that the other way around, now that I think about it. So we hold shift and we can use some keys on the keyboard as well, the bracket keys, to make our size a little bit larger. So let's make all of this grassy, just like that. And now make this a little bit smaller again. And we can like paint in a little bit of a sandy dirt path, with it just being one material. And now we have a grassy material that we can apply throughout the entire game, and on a per mesh basis, we can decide, hey, we want a dirt path going this way or this way, instead of having to break that all down into separate, unique textures, which would be hundreds upon hundreds of textures that we would need, instead of just using the vertex data to loop between the two. And you can go real crazy with this, right? This is a very rough example of what we can do, but in other examples, what you can do is like in a wood material, you can have two sets of texture maps, one for the outside of the wood and one for like the inside, and you can start like painting in some damage. Again, do be aware that you are limited by the mesh resolution, the amount of vertices that your mesh has. So if you have a very low poly mesh, vertex painting isn't going to work too well. As well as if your mesh is nanite enabled, it's also not going to allow you to vertex paint on it, because the vertices on the nanite meshes are constantly being regenerated and streamed from the disk. It doesn't really work with the more traditional way we usually think of geometry. One last thing that I want to point out is we have LOD model painting. LODs, hopefully you're aware, level of details, the further away something is from your camera, the lower poly version of it you can render. Usually when you're painting on this, it will just kind of like guesstimate how to apply those to lower LODs. If you have a object with multiple LODs, you can, if you want to, also paint those in individually depending on the LOD level. It's a lot more work, but it will be a slightly better result. Then again, the point of LODs is that they only are used when things are far away from the camera, so it's most of the time not that. So that is vertex painting for you, and vertex colors. Of course, we can do more than just lerping as well. We can just use like the green channel for the roughness, and now everything on this thing will be very rough, meaning very non-reflective. But if we go back into mesh paint mode and I say, hey, paint, and instead we want to deal with the green channel, probably should set this to white actually. I can then start painting on this, and that will influence the reflectivity. So if we want to have like spots of the grass being a little bit more shiny because maybe it's just rained, it's kind of hard to see on these textures, but right around here you can see there's a little bit more reflectivity going, and then I can paint over that again, and so on and so forth. So you can use this in a variety of different ways. You've got 4 channels to really do whatever you want with in your shader. Let's talk some more about materials with material parameter collections, because we've talked about material parameters and we've even talked a little bit about vertex painting already in the last video. Today, let's talk about something else fun, because these parameters are things that you can use to influence materials on a per instance basis, which is really, really cool. But what if we have something that is almost the other way around, where we have one value that is global throughout your entire project, but separate materials can use that value in different ways? That will be very interesting. And that is what material parameter collections are. So let's make one. We can, in our material sub selection here, we can create a material parameter collection. And let's just call that tutorial params. And when we open that up, we get a list of scalar parameters and vector parameters, which is just singular values and triple values. Let's make one of both. Call this one just scalar. That's fine. And then we'll make a vector parameter as well, which will just be a color. And we'll call that vector for now, just to keep things simple. You can make as many of these as you want, of course, so we can add like a bunch of these, but that's not necessarily what I want to do right now. And these can now be accessed from any material in your game, or any blueprint in your game, technically speaking. But really, mostly they're meant to be used for material stuff, not to store any non-material data. There's other ways to do that. That's not what we're talking about here today. Let's make 2 materials use this data in different ways. So we have this material over here, which is our vertex color material that we made last time. And then we've also got our flat color material that we made in a previous video. Let's add in a collection parameter. And there we can choose out of all of our collection parameters. Of course, we don't have that many right now. We're using the tutorial params in this case. And we have to choose what parameter we're going to be using. So for this example, let's use the scalar value. And in this material, that scalar value is going to drive the metallicness of this thing. I don't know. Let's set the roughness here to 0 so that we can really see the metallic vibes that we have here. So if we disconnect this. So now, if we go into our tutorial params and we go into our scalar, we can set the default value here to 1, and we will see, hey, this is now a very, very metallic value. Even though within the shader itself, we don't really have this value set at all. It's because the material parameter collection has this value stored in it, which we're just reading. Now, let's go into the vertex colors material here. And for this, I think what we're going to do is we're going to let's scroll the textures based on the parameter instead. So we can again say our collection param, and we'll use the scalar as well. And this will just be the speed of that scrolling. So we'll need a time node for that. We will need a texture coordinate node for that. We're going to break that. We're going to then add to that time divided by like 100 or something like that. So every second it's going to move 1% of the texture. And then we will multiply that by our scalar value so that we can say make that go faster or slower depending. Now, this is not a particularly great example of using them because this value we probably want to be able to set to like 5, 6, 7, 12, 15, 127, something like that. and what we're using it for here is really only a value between 0 and 1. So again, not a great example, but you can do so much cool stuff with this. Let's finish off this scrolling that we have here. We can append vector, get the green channel back there, and then use that as the UVs for these two, which will make them slowly scroll. And now we can see that this thing is very slowly scrolling, and these are very metallic. But if I set the scalar parameter to 0, these will stop being metallic, and this will stop scrolling. If I set this to 5, this will still be metallic because it caps out at a metallic value of 1, and this one will now be scrolling a lot faster. So they're both reading the value in our parameter collection, but doing different stuff with them in their individual shaders, which is really, really quite cool. Now we can also access this from a blueprint. So instead of doing it in a material, we can deal with this in a blueprint. And in here we can get the scalar parameter value, and we can get the vector parameter value, which will work much the same way. We pass in the collection that we want to get it out of, then we get a drop-down menu from all of our scalar parameters that we can choose, and the same thing here with the vector parameters. So that way you can also use the variables that your material is using in a blueprint if you needed to. I didn't point it out in the video about the parameters because I didn't think it was that relevant. You can also just get the information from a normal material, their parameters, but the same way we can set the parameter values in here, we can also set the parameter values for a collection. So let's do something a little bit fun, shall we? We can play a timeline, and this timeline we will at the midpoint set to a value of 1, and then at the end we'll set it back to a value of 0, so it's going to be bouncing back and forth between the values. And we can set scalar parameter value, which gets us a collection, our tutorial params, our scalar value, and that we will be setting through this timeline. So now, if we connect this up to update and we play the game, we will see that these things will go from being metallic to being non-metallic. And this thing will, if we get a better vantage point, is going back and forth in its scrolling, which is very, very interesting. It seems to be scrolling back and forth, so it seems like value is actually getting set to a negative at some point. Not entirely sure where that's happening, but that's not really relevant for what is happening here right now today. So there we go. Material parameter collections allow you to use these parameters in different ways for different shaders, which is very, very powerful, because if you have a system like a rain system in your game, right? Some materials might react to rain by becoming wet, having their roughness go down. And some materials might react to rain differently. Like if you already have a water material, you might want to add like little droplets that hit it instead. Or some materials, like if you have dirt, it might not necessarily become more shiny, but it might become a little bit darker because it absorbs the water. All that kind of stuff has to do with rain and can be driven with just the one simple value. We're really getting into it now. We've talked about a lot of stuff. Today we're going to be talking about material functions. What is a material function? Well, if you're used to programming, you know what a function is. It is a little bit of code that is easily reusable elsewhere in your code. And a material function is pretty much that for your material graphs. So if we go into, for instance, our flat color material here, and I add in, I think, a height loop, which we'll talk about in the future as well, you see that this is a different kind of node. It's like this blue type of node. That's because a height loop is a pre-existing material function. You can actually double click on it and it opens up the material function, so you can see how this height loop works under the hood. Of course, we don't really care about a height loop at the moment, but that's just to demonstrate what those nodes are. If you ever see one of those types of nodes and you're wondering, hey, what's actually going on here? You can double click on it, open it up, and there's a good chance that you'll be very confused, because most of the pre-existing material functions in Unreal Engine tend to get quite complex quite quickly. But we can make our own as well. So if we go into our materials here, we can make a material function. And let's just say that this is like texture, coord, scale. That's something that we do quite a lot, right? It's just scaling up and down our texture coordinates. So if we open this up, we get a output node, which is whatever we're going to end up outputting. And that will, in this case, be a vector2. So we'll get our texture coordinates, and that will be a vector2 that we will multiply. Actually, let's break the texture coordinates first and then multiply them by two different amounts. So we get an x and a y thing. So we can scale them in different ways, and then we can append them back together to make it back into a vector 2. And that will then be our output in this case. And now it's just multiplying these by 1 at all times. So instead of just adding a normal parameter here, like you'll be used to in a normal material, what we want to do is actually we want to add a function input, which by default will try to add a vector3 input. But if we go over to the input type over here, we can see we have a input type that we can put to anything that we want aside from that. So if we set that to just a scalar parameter instead, or in this case, actually, let's just make it a vector2 because that makes most sense. We're working with a vector2, might as well make this a vector2. There we can break this one as well, and then the R will multiply with the R, and the B will multiply with the B. We can even give this a default value, like a preview value, and we will just ignore the Z and the W slots here. It still displays them, even though this is a function input for a vector2. It's only going to take in the first two parameters that we have. So we'll set those to 1 by default, and now we have our little material function here. And selecting the outputs here, you can give this some kind of name. I called this one scaled UVs, because that's what the output is called. We can also give the inputs a name. I'm pretty sure, yeah, input name will just be scale vector2. In this UV math material that we made sometime in the past to show you UV math, we made this like texture coordinate divided by 10, and that's then going into the texture sample to set the scale of this texture, right? But now that we have our material function, we can disconnect this like it was just a moment ago. So instead, now we can drag our texture coordinate scale material function into this material graph, and we can simply supply it with a vector2 value. So we'll just set that to 1 and 1 for now, and you can see how easily that works. But we can also set this to like 10 and 10, and it will multiply our texture coordinate input very, very simply. To get the same result that we had before, divided by 10 is the same as multiplying by 0.1. It's just basic math, and we have the same result that we had a moment ago. And as you could see there, we can also very much just say, hey, we want to only stretch in one direction, just like you can with any other like stretching and squashing with UV coordinates. So this is now all inside one node. What is very interesting though is if we have a parameter in here. So for instance, we could parameterize this if we wanted to, and run that through the texture coordinate scale. Just like convert this to a parameter and call this param UV scale. And now if we make a material instance on this, we can just scale this up however we want, right? We've gone over this before, so let's make a material instance of this real quick. And we can see that we have the UV param scale, and that is for some reason taking in a vector 4. I don't exactly know why, but we've gone over this. That's because apparently when you make a parameter out of a vector 2, it just turns it into a vector 4. I'm not entirely sure why it would do that, but it does that. Point being is that instead of doing that, what we could do instead, if you wanted to, is not have a input here. We can just remove the input altogether if we wanted to. And we could instead, for the most part, you probably wouldn't want to do this, but this is a thing that you can do, is we can make this into a parameter instead. And then all of the materials that use this material function will have access to this parameter. Because the material function, at the end of the day, is kind of just a bunch of nodes crammed into one node. You could just as easily just put all of the nodes from any given function into a material graph, and that will be effectively the same. So that also counts for parameters. So if we count this as a UV scale param2, it's important, just like with any parameter, that they do have unique names. We can break the 4 components. Again, we're going to just ignore the B and the A here. But now if we hook these up like this, making sure that we have the proper ones connected up, we do not. Something like this, maybe? Things are being a little bit weird. Even though this has 4 values in it, it says that I have to use a float 3 components break node. So sure, let's do that. I don't really care. And we can hook this up to there, this up to there. We can just ignore the B. And now that we have that all set up, if we make sure that everything is properly applied and saved, we will now see that we have the UV scale param 2 instead. So we've got the UV scale param, which is actually not hooked into anything right now, so it's not being taken into account. We can now directly influence the scaling in the material function instead of doing it through the multiplication that we did before. Now, for the most part, I think it is a little bit better form to not use too many parameters in material functions. If you have a reason to do so, please go ahead and do use them. But for the most part, I think you want to mostly stick to function inputs instead, unless you know what you're doing and you have a really good reason to want to use a parameter. There isn't all that much to this with the whole material function thing. Aside from, of course, you can put material functions in material functions as long as it's not the function that you're working in. So what you probably shouldn't do, I don't even know if it will let you do that. Let's try this out. Textual coordinate scale into textual coordinate scale. I can't use the material function as it would cause a circular dependency. So yeah, because that would then call this function within this function, and that kind of just melts your CPU. So don't do that. You can't even do that. But if we had a separate one, so let's just duplicate this and call this a textual coord scale 1, we can very much just drag that into here, and then we can have like multiple layers of functions that call other functions that call other functions, as long as you don't make a loop of a function calling another function, which that then calls that first function again. But as you just saw, Unreal has built-in protections against that. So if I now, even if I go into texture chord 1 here, I shouldn't be able to put in the texture chord scale proper. Actually, I am. That is interesting. Potentially, like when I save this, it's going to, yeah, it's not going to allow me to do that because it says, hey, you're trying to call this other function, texture scale 1. It's not going to allow this because it says, hey, the function you're trying to call also has the function that you're working on right now inside of it. So that's going to create a loop, and we're not about having those loops. So you can't even do that. It's a fun little tool to be aware of, to be able to use going forward. In this series, we're not going to be using it too much because this is mostly to make more complex materials a little bit more readable, but we're not really building any very complex materials in this series. We're just going over all of the individual aspects of the material graph. So we've covered this now, don't forget it, and we'll be moving on. Oh boy, I've been waiting for this one. Custom data. Custom data is something else entirely, man. We've talked about parameters before, right? We've got all these materials over here, which are material instances, actually. So that's a bad example. The dynamic material instances, rather. But we've got like our flat color material, which has this color parameter for the base color, and then it's got like a collection parameter as well. I've done a video on that. Go watch that. And then we've got a different material instance for each color that we could make. We've also covered how we can use that to dynamically set new material instances. But I also warned about how computing intensive that actually is. Because we're using the same quote-unquote material here to make these 3 different colors. But what is actually happening under the hood is, for all of these, if we open up the blueprint in the construction script, we're creating a new dynamic material instance. So we're not just creating a new material instance, it's dynamic, meaning that it like can't compile things down into constant values. Things have to keep open as variables, meaning that they're going to be more computing intensive as a result of that. So these are three separate pretty heavy materials, comparative leaking. But what if we could have a way to actually just have one material show up as different colors or do anything else with that data? Well, lucky for you, that is actually a thing that we can do. So instead, let's go into our flat color and let's make a separate material for this. So flat color custom data. And if we open that up, and go into this parameter, we'll also get rid of the scalar for the metallicness, because we'll do the same thing for the metallicness, I think, here. And maybe we'll also do the same thing for the roughness, actually. So let's add two more scalar values, convert them to parameters. We'll call this one metal, and we'll call this one roughness. Doesn't really matter what you call them, actually, for what we're going to be doing with them. But let's just set both of these to like a default value of like 0 and then 0.5. We're going to turn these parameters into custom data. And the way we're going to do that is we're going to set in the parameter. So we select the parameter and then we go down here to the details panel. And there you will see we have this little section called custom primitive data. And we're just going to check this tick box. So if we check that tick box, it's going to give us some new options here. And that is the primitive data index. What does that mean, you might ask? Well, let's actually just draw that out real quick, because the custom data is going to be stored in an array. So what it'll do is it'll store them all as float values. And this data index that we have over here, this will just be the starting point of that index. So if we have a color, that is going to be 3 floats, and it's starting at index 0. So we have index 0, index 1, and index 2. These are going to be holding the R, G, drawn with a mouse, give me a break, and B data for our colors. Then if we have more custom data, we don't want those to be stored on indexes 0, 1, and 2, because those are already in use for our RGB data. So our metallicness, for instance, will be stored on number 3. So we'll call this metallicness. And then on index number 4, we'll store our roughness. But you do want to be a little bit careful about how you order these, because you're likely to use the roughness value here a lot more than we end up using the metallic value, because the metallic value we only have like actually set to 1. The default will be 0. We want to set that to 1 when something is metallic, which is not that often. Like most of the time, it's actually not. But in order to get to the roughness value, which we'll show how to do that in a moment, we need to add all of these indexes, including the one that we're using. It's just a float, so it's not that big a deal on a small scale. But you probably want to order these from most important to least important, so that when you want to access any of these, you can easily access only the ones that you're going to often need without needing to add indexes for stuff that you're not going to be working with. So this will be index 0, 1, 2, 3. Oh, it's actually a vector 4 because it's also got alpha. So bump everything down one index. But if we then go into this and we set this to custom primitive data as well, this is also going to be using index 0. So that can be interesting, right? We can, for instance, if we wanted to, and we set this one to primitive data as well, we can maybe, if we really want to, like make this share a data input. So if we both set these to 4, you can see it actually displays it on those nodes. They're both going to be getting their value from 4. So if we set this to 1, we're going to have a very metallic and a very rough, so very non-reflective material. If we set this to 0, we're going to have a very reflective, non-metallic material. They will be linked to each other. And we could do something clever with that, doing this like a 1 minus, so that it negates it, makes it negative. And this will now make something very non-reflective and very non-metallic, or something that is very reflective and metallic due to just having it both be on custom data index 4. let's actually keep it at that for now. Maybe I'll come back to this and set the roughness to 5 just to show you. But for now, I think what we want to do is we want to show you how to actually use this data. We can still set a default value for this, I'm pretty sure, maybe. Maybe not, I don't know. So let's use this material on these blocks instead. We've had these blocks hanging about for a while now. I think they are not just static meshes. Never mind, that's not going to work that well. What we're going to do instead is we're going to just simply add a couple extra cubes here. So let's just add in a cube here, and we'll add in like 2 more cubes just for shits and or giggles. And those are all going to be using our new flat color custom data material. And as you can see, they're all black because that is the default value that we're working with here. If we select one of them and we can just look for custom, we have rendering, custom primitive data defaults. And we can add some array elements here, which adds the values for whatever we are working with here. So it adds R, G, and B, and A. And then it adds the value for metallic and roughness too. I think that these are little previews of what indexes exist for this. Might be new. I haven't seen those before, but I don't use this too much either, if I'm being honest with you. I should do as I say, not as I do. It even gives you a little bit of a warning, like, hey, metal and roughness are both being driven by number 4 here, and you probably don't want that. But we can now set this to 1, and you should be able to see that it is a very bad example because it's black. Let's set that to like red. Or actually, let's just set it to white. Just setting everything to a value of 1. I don't know if alpha is going to really help with that. But now you can see that this is a very reflective, like chrome-like color. If I set the metallic and roughness both back to 0, it's just a opaque, flat white color. Let's set green back to 0. Now it's a pinkish color, and so on and so forth. And now I can go into this one, and I can add maybe only the first 2 array elements, because I only need the red and the green data, because I want to set this to like 60% red and then like 30% green, which will make a very like yellow color. And we don't even need the blue channel here, let alone the alpha or the metallic or the roughness. Now, if I add the metallic value, you will see that it automatically does add in the other indexes before it as well. So I can't just say, hey, I only want the metallic roughness or I only want a green channel, because the moment you add an element, it adds all the elements before it as well, because it simply just needs that info. But the wonderful thing now is that these are all the same material. They're not dynamic material instances. They're not even material instances at all. They're just the same material, rendering with different custom data. And there we get into, I lied a little bit to you before because we were just getting started with this whole material thing and I didn't want to overcomplicate things. We're going to overcomplicate things a little bit now. What I said before is that the material instances will be more performant for your rendering, which is still the case because it renders the material instances all at the same time as the parent material. And that is not actually 100% accurate. It's a good enough understanding for a like basic level, knowing that material instances make you more efficient in your rendering. But it's not exactly because of the reason that I said. The reason that I said actually applies to this, because these are now using the same material. They are being drawn together. They're being instanced together and being drawn as one thing, which reduces your draw calls, and your draw calls is usually going to be the bottleneck of your renderings. Okay, I'm jumping in here real quick during editing to explain the whole draw call thing a little bit more, because I kind of skipped over that, so let's talk about it. The amount of draw calls we have is dependent on 2 things. Number 1, it is the amount of meshes that we have in the scene. Do excuse my bad handwriting, I'm writing with a mouse right now. We also care about the amount of unique materials that we have, and that does include material instancing. So if we have like material instances, every single one of those does count as a unique material for draw call purposes. So these are the 2 things that we want to look at. And when I say meshes, I mean unique meshes. If you have the same mesh 2, 3, 5, 100 different times in your scene, those still count as one mesh. That is the entire point of what we're doing here. Because if we have just one mesh, we're just making a game out of entirely only cubes, for instance, right? We're making Minecraft. That is just one mesh, but we might want a grass block, and we might want a sand block, and we might want a separate dirt block, and a stone block, and a magma block, and whatever. Right now, that makes us up to 5 different materials. Those can be material instances because they have the same properties, but they have different texture maps, so they need to be material instances. So we have one mesh, but that same mesh is rendered with 5 different materials across our scene, meaning that we just multiply these together to get 5 draw calls in total. And again, this mesh can be like instanced 1,000 times and use those different materials on different instances of them, and that still results in only 5 draw calls. So that's really, really good. But now, let's say that we want to have green grass and slightly more brown grass and entirely like dead, very brown grass. Are we going to add 3 more materials to this list, or are we going to change our grass material to use custom data so we can save some draw calls on that? Because that would be a total of 8 materials now, still with just one mesh, that is fine, which is now a total of 8 draw calls. Again, the amount of instances does not really matter. But now let's say that we want the magma to have a couple of different tints as well. Maybe like very hot magma will be more orange and cooler magma will be more red, and we have like a couple of things in between. And now suddenly we're up to like 11 or 12 different materials, still with only the one source mesh. And that means that we're now using over double the amount of draw calls already. Well, we haven't really added any new materials. We've only added variations in color on existing materials. And this is where the custom data thing comes in. Because if we use custom data on those materials, so that probably does mean that they're not going to be material instances because they have different like math going on. But this is the important part. Don't get stuck on trying to make a material instance when you can try to make a separate material with custom data instead, because that actually does save you more computing power in the end. Because now we have a grass material and a magma material that we can use endlessly for various colors that we want to. If we have like a glass block in Minecraft, like you have 16 different types of glass, right? All the colors of the rainbow and then some. Those could all be in one material with just some custom data. So those don't need to be 16 materials, meaning that you have to have 16 less draw calls or 15 less draw calls, I suppose. And with these like very small numbers, that does not really matter that much, right? Because we're down to like 10 draw calls, 20 draw calls, who cares? But now imagine that we don't have just one mesh with 5 materials. Now imagine that we have 100 meshes with 5 materials instead. Depending on how those meshes and materials are applied to each other, if every single mesh has a version with every single material, at the very worst, we would have 500 draw calls, because you can just multiply those together to create the amount of draw calls that you can, at the very most, expect. And now you can suddenly see, okay, but if we have like 15 different materials for simple color variation, we're going up to like 100, potentially, again, times 15. And that then creates suddenly 1,500 draw calls, meaning that with a little bit of clever custom data use, we can save 1,000 draw calls in this scene, which is going to be a noticeable difference. And if we have even more materials like the glass that I just mentioned, we can either add just one material to this, making this 600 draw calls, or we could add 16 materials to this, making this up to 3,100 draw calls. Just adding some color variations in our glass more than doubled the amount of draw calls. That's 1 0 too much, I'm sorry. Still, 3,100 is quite a lot. So you can see how when you scale this kind of thing up, trying to optimize some materials to be able to be used in multiple different ways, like you don't need to have a material for a reflective version of something and a normal version of something. Even with material instancing, you don't need to do that. You should use custom data for that, because if you're doing that for every single material in your game, you're suddenly doubling, tripling, quadrupling, 10 timesing, whatever your draw calls. And that is the thing that's actually going to be killing your performance. So I just wanted to jump in here and give you a little bit more background and a little bit more math. I'm sorry about that. About the draw calls and what to keep in mind. I've talked about material instances before and how important they are, and they can be really important and they should be used wherever you can. But if for any reason you're like, but in this case a custom data would maybe work better, a single separate material with custom data, if you're going to be using it a lot, often is preferable to a lot of different material instances. The upside of a material instance is if you have very complex parent materials, it just saves some memory. It is really what it comes down to. Because if your material is like very complex and its like data total is like 5 megabytes, which might not sound like a lot, but imagine if you have like one material here that is 5 megabytes, and you have like 100 materials that pretty much do the exact same thing, just have some different parameters. And those parameters are individually a matter of a couple of bytes, unless they're textures, in which case they might go up to like kilobytes, in some cases maybe even megabytes. You don't need to store the exact same instructions in your video memory like 100 times, right? You can just store those instructions once and then only store the parameters for the rest. That is what material instances do for you. They make you a little bit more efficient with your video memory, more so than really saving you any actual render. That is what custom data does. This is still a very brief overview. Of course, this is still an introductory material course. Materials and rendering are very complex, okay? We're not going to do a very deep dive into like how the code works, because frankly, I only have a surface level understanding of that myself, because you don't need to know it in a very deep, in-depth way. You just need to know what bits and what techniques deliver what performance impacts and how to avoid them and what the alternatives are. So, custom data. We've done it with color now, we've done it with metallic and roughness. You can do a lot of creative stuff with this. Again, you can combine some things into like the same index, the same like custom data channel. You're not supposed to. The engine really doesn't like it when you do that because it starts screaming at you, but you definitely can. Like, it's not going to stop you. It doesn't actually cause any problems. It's just, it doesn't expect you to do that. So go ahead and have fun with some custom data setups. Let's talk about some height lerping. This is something that I've wanted to talk about for a while because it's some really cool stuff, and now that we have pretty much the most basic stuff down, let's do something exciting, and then we've got some more basic stuff to cover after this, don't get me wrong, but for now, let's do something exciting. Height lerping. What is height lerping? Well, it is lerping based on height. That's been the video. Thank you for watching. Okay, now let's get going with this. We're going to probably just use this material that I have right over here. If I can remember which one that is. It's the one that I use to show vertex colors. So let's stop doing this whole scrolling thing because we're not going to be using it anymore. And none of this we're going to be using anymore either. Don't mind all that stuff. If you haven't been following along with the series as a whole, it's not that important. So we've got these two little textures here and we're looping them based on our vertex color red, right? We've covered that before, like this is all red and this is all not red, or the other way around. I don't remember right now. If we just apply this, it will stop scrolling as well, which will look a little bit better. But what if we have something like a maybe like a brick texture or like a tile texture or whatever, where we want like moss or grass coming through the cracks only, or the cracks first before also covering the bricks themselves. That is where height lerping comes in. Height lerp, I think I showed it off in an earlier video as an example of a material function, but we can just add in a height lerp node again. You can just reconstruct this yourself if you want to. You can look into how the math behind all this works and check out the material function itself here, but we're not going to do that. I'm just going to show you how it works. So we have two inputs, A and B. We have a transition phase, which is going to be in our case the vertex color, but you can do this with like a texture or whatever you want. Then we have a height texture, which is quite important, and some contrast for that height texture. The output will be the result of the looped A and B based on the other things given in. But we also get a alpha out, so if you just want to use this as a alpha to put into your existing loops, that's entirely possible. And we got a loop alpha no contrast, so that's a softer version of the alpha. I'm going to show you with the height loop A and B input first, and then I'm also going to show you with the alpha. So instead of using this loop that we have right over here, let's get rid of this for the moment. What we're going to do is we're going to replace it with a height loop. So input A is going to be texture grass, input B is going to be the texture for the dirt, and then the result is going to go into the base color. You will notice that it does throw an error because it does need a height texture. That is one of the required inputs. So let's just give this like a Perlin noise as a input for the height texture. And now we can see this is entirely 100% just grass, because of course the preview doesn't have any vertex painting. But if we just make this into a separate window real quick and we go into the third person example map, you will also note that I didn't put in a transition phase because I am an idiot. Let's put in the red vertex data. Now it's entirely brown because we don't have vertex colors. But if we go back here, that's more or less the exact same thing that we had before, isn't it? Well, it kind of is. But now we get to the interesting part, right? Because this cloud texture doesn't really do that well. Maybe if we add in the UVs here, maybe it'll make some difference. Not really. So if instead of using the vertex data colors, I don't know what happened there, we use just a scalar value here in the transition phase, I'll be able to show things off a little bit better. So if we set this to 0.5, for instance, we should be able to see that it's coming through with the other texture everywhere that the value is 0.5 or below. So if I set this entirely to a value of 1, you will now see that it's entirely the B input that we're working with. And that's all driven by the height texture. So if we had something that is a little bit more, do we have like a tiling texture or something like that? I guess we can use this widget grid vertex as an example, because it's got a lot more contrast to it naturally already. So now we can see like 0.5, everything that is below 0.5 is going to be texture sample A, and everything that's below 0.5 is literally just the black squares that we have here, and that's all going to be the grass. Everything that is over 0.5 is going to be input B, which is all of the lines here, which is our dirt texture. Now if we go back to tiling noise and we add in a little bit of contrast here, so let's add like a contrast value of 3, so it's a little bit less soft. That makes this entire effect a little bit more noticeable. And if we convert this to a parameter, so we can actually change this in real time, we can see if I change this parameter around now, we can have this really nice like height lerping effect where one material starts to like fade in based over the other material based on the noise texture that we have, which is really quite cool. Now, the issue with this is we have to do this for the base map, and then for the metallic map, and then for the roughness map, and for all the different maps, right? Which can be kind of annoying to hook up. So what we do instead is we actually can just use the normal lerp, and instead of using the result output here, we don't even need to supply any inputs for this. If we're doing it this way, we can just put our inputs through our normal lerp and then use the alpha output from our height lerp into the alpha of the usual lerp that we have here. And this way we can very easily also like lerp the normals, for instance. So let's set that up real quick. Let's make a little bit of room to set things up here. We'll keep the noise texture, that's fine. And then like copy these two over, and let's see, hopefully we just like have the grass normals and the sandstone normals as well. And we can very easily now also lerp these two in much the same way with just the same alpha outputs. Do make sure we use the same texture coordinate systems for them. Otherwise the normals aren't going to line up with the textures. That would be bad. But now, just as easily as that, we have a lerp that we can put into the normals. And now the normals of these materials as well as the base color textures will be driven by the same input, which again, for us right now, is just a parameter. So we have this parameter here. Let's apply this actually so we actually see the normals. We can very slowly fade between the two, and it fades between the normal maps included as well. And of course, we're doing this with a parameter at the moment. Realistically, you'd probably do this a little bit more with a vertex color. So let's do that again, putting that into the transition phase. If we apply that, we can now see that we have this slightly more harsh edge due to the contrast we have in the height lerp. But if we go into mesh painting, and I set my paint to, instead of having a strength of 0.5, which is quite strong, if I set this to a strength of like 0.2, we might see there's a little bit more like smoothness to the way that this applies now, and it doesn't apply everywhere. So in some cases, we just need to go over this a couple of times in order for this to actually take. Like we can make this apply everywhere. We can also set up a material where it will just refuse to lerp anything beyond a value of like 0.8, whatever, in the texture. It's a little bit more complicated, but we can do some really like neat stuff with this. So if we, for instance, go back to the grid here, that'll make that a little bit more noticeable. You'll be able to see that drawing this in now, we very easily draw in the little lines, but if we want to draw in the squares themselves, that takes a little bit more application. We can even set the strength even a little bit lower, so it's very clear that we can draw in the lines here a lot easier than the squares themselves. Like if we just keep drawing onto this, we will eventually start drawing onto the squares, but that just takes a lot more until we get to the value of 1, at which point it switches over to the other material. But for everything in between, the actual lines, any value that is like above 0 pretty much should give you the underlying material here. So that's how you can basically use the height lerp. Do excuse me if I mixed up the saying above a certain value or under a certain value at certain points to do with the transition phase. I get it mixed up in my head all the damn time, whether or not the transition phase is the value, like which direction the lerp works. And if I had to guess, you're also going to run into that issue because it's just like not particularly intuitive. And it's also not that relevant because when you notice something is wrong, you just swap things around or you start using a different vertex paint, like you start to subtract instead of add, and that ends up being fine. So just experiment with it a little bit and you will start developing some intuition for how this actually works. Who among us failed high school math? Because if you did, you're not going to like this one, but it's a very important video to cover. We're going to be talking about sine and cosine and the time node, because those really play into each other. I think we've already talked about the time node before, so I'm going to just go over that real quickly. Time in your materials here, let's just use the vertex color material that I've been working with over the past couple of videos. Time is simply a value that we can use that returns the amount of seconds that have passed since this game started. It's just that easy. So, for instance, if we were to be insane and put the time into the emissive color, we're going to get a very shiny thing that gets more and more shiny as time goes on. So if we apply this, yeah, we can see that this gets quite shiny quite quickly. We don't necessarily want that, but just as an example. What we do instead is usually we add a time node when we're scrolling through a texture, like panning a texture or whatever, all with a sine or cosine node. If we want to do any like modify time, we use the time node, we do some math on it, and then we put that into the sine or the cosine node. Now, what does sine or cosine do? And I very much like that question. And for that, we're actually going to go back into our flat color material that we have here. I suppose we can use the one that I used the custom data on, but I think I prefer to just like use the normal flat color instead. Sine and cosine are pretty much the same node. It's just a matter of where they start. And you might be thinking, what the hell do you mean with that? Well, sine and cosine are just nodes that make a curve. And that curve, this is actually like not horribly drawn, goes from a value of +1 to a value of -1 in a certain time period. With, of course, like the middle line here then being like a value of 0. The only difference between sine and cosine is that cosine starts here and sine starts here. Or it's the other way around. I can never remember. Because much like the direction of the height lerp, it doesn't actually matter that you know this by heart where they start. It's just, in most cases, they're both applicable. Sometimes you want to start with one position. Sometimes you want to start with the other position. It doesn't really matter that much. Usually we just use the sine node. And there we have the period, which is the amount of time that it takes to go from 1 to -1. So if that's 1, it's going to take 1 second to go from +1 to -1. Very often, we don't actually want to go from +1 to -1. Very often what we actually want to do is we want to go from 0 to 1. And that is where we just simply use the remapping node. This allows you to put in a high value and a low value. The default for the input value is 0 to 1, and the output will also be 0 to 1. What we're going to do is we're going to say, no, our low value actually is -1. So this makes whatever we put into here, it's expecting a value of -1 to 1, and it's going to remap that to a 0 to 1 value. So now we have a sine wave that effectively just goes from 0 to 1. You can also do some more manual math, which is probably slightly more efficient. What you can do is you can simply add 1 to it. So now it's going from 2 to 0, and then you can divide it by 2, and now it's going from 1 to 0. This does the exact same thing. It's just some more simple math. The remap value range does a little bit more math because, of course, it takes in variable amounts. If you're following along with this math, this is technically better. If you can't be bothered doing this, just use the remap node. That's entirely fine as well. And we can now use this as a 0 to 1 value for the alpha of a lerp, for instance. So let's add linear interpolation, the alpha, and we're going to be looping between, I'm just going to do 2 constant colors because we don't need those to be like parameters at the moment. And we're going to be looping between like blue and fucking magenta or something like that. Now, the sine node is not going to work too well if it doesn't have an input, and for that, again, we can just use the time input. This is going to flash quite quickly back and forth between the two. As you can see, it's going back and forth between the 2 colors. Now, if we divide our time by like 2, it's going to be fading back and forth a little bit slower. If we divide it by like 100, it's going to be fading back and forth between the 2 of them quite slowly. I'm going to keep talking here, hoping that at some point you're going to start noticing that it's a little bit more blue now than at the beginning of the sentence, but this is actually like taking quite a while because dividing it by 100 actually means that it takes 100 seconds, which is like about a minute and a half to change from one color into the other. So we're actually just going to set this to 10 instead, and now you can see the effect more subtly happening, but you can actually see it happening. So for color looping, this is a very cool thing, but you can do this with like everything, right? Instead of just looping the colors here, what we can do is we don't even need to do a loop for this, to be honest with you. Well, we can use the alpha and then also put that into the roughness. So now, as it fades between these 2 colors, it's also fading between being reflective and being non-reflective, which is a very, very cool effect. So there's a lot of stuff that we can do with this. Sine nodes, cosine nodes, together with like the time input, are also often used for like foliage wind movement, because we can do that in the shader. We have our like world position offset. So if we take that world position offset and we just get a like vector 3, which is only in the up direction, and we multiply that by like a strength amount, so let's say 100, and then we multiply that by our sine. But this one doesn't have to be like normalized between 0 and 1, because a world position offset can just go into the negative as well, so we'll just use our normal sine to multiply that with, and then we put that into the world position offset. we now see that it's also going up and down as we go along with the sine as well. So you can imagine putting this into like a dynamic parameter. For the strength that we have here, we suddenly have options to make like leaves moving back and forth very, very easily. So anything that needs to cycle and bob back and forth between two values, that's kind of where the sine node comes in. And again, we can technically also use cosine for all this because it works the exact same way. We can put in cosine here and there and like there as well. And you see this works the exact same way. It just starts at a different position. So for the most part, like cosine isn't actually that relevant, or sine isn't that relevant. No matter what you use, you'll probably be fine. Usually I end up just using the sine. So this is a quick little overview of how you can use sine in combination with time to make things lerp back and forth. Right now we're lerping between color, between roughness, and between positions all at the same time with the sine and cosine node because they're all being driven by the same thing. It's a really quite cool fact, and you're probably going to end up using this quite a lot. Let's talk about some more fun stuff today. We're going to be talking about the Fresnel node. Last time we talked a little bit about sine and time, which are very important concepts. Today, let's talk about something that's a little bit more niche, but still very, very cool to actually look at. So for this, we're going to just make a new material real quick, which I'll just call something like material Fresnel. You spell it as a fresnel, but it's a French word, so you pronounce it as Fresnel. You can pronounce it however the hell you want, to be honest, I don't really care. So what does the Fresnel node do? First and foremost, let's just get it up on the screen here. So we have an exponent in and then base refraction in. And now we've got the normal. So let's put this into the base color and see what happens. We get a dark orb with a light fringe on the edge. If we set this to unlit, you can see it a little bit better because the lighting isn't messing with it. So you might be thinking, okay, so this is something that has a 0 to 1 value from the center to the edge of an object. And then I will set this to the cylinder preview type and it suddenly looks a lot different. There's suddenly no highlighting here at all on the top and the bottom, only on the edges. If I set this to the cube, it kind of almost doesn't do anything. On very glancing angles, you can see a little bit. Again, do be aware that this is an unlit, so this is not lighting bouncing off. This is the Fresnel node itself changing the color of this surface. So what does the Fresnel node do? In the simplest terms, the Fresnel node gives you a value on how perpendicular of an angle a normal is to your camera normal. So if we've got like our camera here, so let's just draw a little camera. This has a normal, which is just the direction that this camera is facing. If we then have a surface here, for instance, a cube, so let's just draw a very bad cube real quickly, right? All of these surfaces also have normals. So this one points that direction, this one points that direction, and this one points that direction. The more perpendicular these normals are to the normal of the camera, the higher the value will be on a scale of 0 to 1. So if we are looking straight onto a face, so again, let's draw a cube here real quick, and I will definitely like get all of the awards for my incredible art skills. So if our camera is looking straight at this face over here, this is going to be entirely black, entirely 0. At the same time, this face over here, let's just draw a quick little arrow to it, is going to be entirely white. The thing though is, if we're looking at a cube, you're not going to be able to see the top and the bottom face when you're looking at one of the side faces, because that's just how geometry works. Unless you have a very wide field of view, in which case you might be able to glance some parts of it. So for cubes, this doesn't really work that well. But now if we have a sphere, which is a lot harder to draw in 3D, because a sphere is just a circle, and I'm not going to be shading this, but if we have a sphere, that suddenly works a lot better, because we can see a lot of individual faces, all with slightly different normals. And if we look right at a sphere, we can still see a lot of the faces pointing in damn near perpendicular directions. So for spheres and curved surfaces is usually what we use Fresnel nodes for, to highlight those edges. A pretty famous example of how you can use something like this is the edge highlighting that happens in Breath of the Wild, in the Zelda game, right? We have these little edges to make models stand out a little bit more against the background, and something like that you can do with Fresnel. Another good example of something that a Fresnel node can do is something like this Spirit Bomb. We all know the Spirit Bomb. It's got this very bright inside, and then it's got this little blue fringe on the outside. Doing something like that in 3D, you would do with a Fresnel node. So in the Dragon Ball games, I can pretty much guarantee you the Spirit Bomb, and probably a lot of the beam attacks actually, are using Fresnel nodes to give that little bit of a highlight to the edges of the attacks. And the upside to using a Fresnel node is that because it's all normal based, it actually works from any given direction. Whatever direction you're looking at this attack from, it's going to have that little highlight on the outside, because that is how things are calculated. So let's dive back into Unreal Engine here, and I'm going to go back in the material preview for a sphere, because again, that's mostly the shape that works with this the most. And we're going to, instead of using this for the base color, what I actually want to do here, and we'll go back into lit mode, why not? We'll set this material here, instead of from opaque, I'm going to set this to translucent. Because one thing that I personally like using Fresnel for is using it for the opacity. Because now you can see we've got this little thing that's see-through except for on the edges. And then of course we can give this any color we want. So let's make a Spirit Bomb kind of deal, right? Let's make this a little bit blue. And we can see we have this little blue fringe on the outside. Everything else is entirely invisible. It's not very much like a Spirit Bomb, because that would be entirely opaque all the way through. We'll get back to that in a moment. I just want to show you a couple of other things. Because we can make this into more of a soap bubble as well. That's kind of what it is already, but we can see through it a little bit too much. So if we go and look for refraction, we can set the refraction method to refraction of index. And that will enable the refraction output pin in our material. Refraction index of different surfaces, you're just going to need to look up. Water, I believe, off the top of my head, is 1.333 repeating. And then you've got other material properties. This is just a physics thing, right? This is just how things are in the real world. They're categorized with a certain number. We're going to go with 13333 for now. And we will multiply that with the Fresnel. So actually we'll multiply that with the Fresnel with 1 minus x. If we 1 minus this, it's actually quite a cool effect in and of itself. We'll have the exact opposite. We'll have a very opaque center, and it's going to get more and more transparent as we go toward edges. And that's what we want for the refraction here. So we'll use the opacity right from the Fresnel node. We'll 1 minus this, and then multiply it by 1.3333 repeating. And then put it into the refraction, and that should give you a little bit more of a refracted look. And you can see it happening a little bit. If you can't see it happening, you want to go into your settings up here in your engine scalability. If you have this set to medium, for instance, you can see it doesn't actually do refraction on medium properly. I think setting it to high or epic will make you use the refraction. So if you want to know specifically which of these settings impact the refraction, it is the effects. If we set this one to medium specifically, you can see there's no refraction. If we set this back to high now, we suddenly do have the refraction. So we can actually just set everything to medium and just the effects to high, and we still have the refraction going on here. So this is how we can make a little bit of a glassy bubble kind of feel. I always like doing this, but we're going to go back to an opaque material because we're going to make something like a Spirit Bomb, I believe, just because that's kind of awesome. It's gonna be a very simple Spirit Bomb. I don't want to set your expectations all too high. So let's set this back to opaque, in which case we might as well also make sure that our refraction is set to none again, because we're not going to be refracting anything. And this is simply just a matter of, instead of using the base color, we're going to be using the emissive color output. And we're going to be using the Fresnel here as the alpha for a lerp. So we can lerp, use the Fresnel as the alpha, and then have this as the A color, and then we have another color as the B color. So let's set that to like a darker blue, maybe a purplish, I don't know, evil spirit bomb. Emissive color, and this is the wrong way around, I think. We want this to be the A color, and then that to be the B color, maybe. Yeah, there we go. So now we have this little thing where the outside is tinged blue. Maybe we want to make this just a little bit like more blue because it doesn't actually work all that well. But we're getting somewhere, right? And we can apply a lot of like noise textures to this to give more, well, texture to the entire thing. But we've gone over all that, so we're not going to be talking about that too much. What I do want to talk about is how to influence the edge here. So let's unhook the emissive color for now and just put this directly back into the base color. And we're going to set this to unlit just to show you it in the best way possible. For the most part, it's just the exponent in that we want to care about. If we set that to being lower, you can see that the gradient is a lot smoother. If we set that to be even higher, you can see it's even a sharper edge. So the default value I think was 4, maybe 5. I think it was 5. So let's set this like to 2.5, having a little bit more of a gradient there. You can see the base refraction index. That is, again, similar to the refraction index that we just talked about for the actual refraction of the material. Usually you don't really want to touch this too much, but you can set this to like a lower value and we'll just see what that does. That also kind of offsets the sensitivity of the entire thing. So if we set this to like 0.5, an insanely high number, the entire thing is going to be like white. Again, the default value here is 0.04. So if we set this to 0.1 even, you can see it's kind of like a general offset that you can apply. If you just set this to 0 altogether, you see that it gets a little bit darker. I generally just would advise to keep your hands off of this. Now, the Fresnel normal actually is interesting to work with, because if you don't put anything into this, it's just going to use the normal from the actual geometry. It says it here, defaults to pixel world normal if not specified. So this uses the normal, not actually of the geometry, but also of normal maps that you have applied to this thing. So if we like get a texture, and we get a very noisy normal map here, and we put that into our normals, we should be able to see that that also impacts the Fresnel node. So the more detail you have either in geometry or in normal maps, the more you're going to get out of this Fresnel node as well. But also do be aware, if you don't want that, you probably don't want to be using normals. Or rather, you don't want to be using the Fresnel node with the default input, because you can input custom normals in here. So if we, for instance, just input a vector 3 with a z value of 1 and put that into the normal, we're now going to get this weird effect where it's not comparing each individual face's normal, with normal maps applied of course, to the camera direction. It's comparing the camera direction to the up normal. So if the camera direction is the up normal, we see that it's black. If the camera direction is a sideways normal, the entire thing is now entirely white. And if it is the down normal, it is also entirely white. So that doesn't like go the other way necessarily. And you can do really, really interesting stuff with this, right? So if you do want to do this like based on geometry, for instance, but you don't want the normal maps to be influenced at all, what you can do is you can just get a world space normal. You can see that still works the exact same way. But if we get the world space normal for the vertex, instead it's going to be doing it purely based off of geometry. So it's going to be ignoring the normal map now. Again, this is just what it uses by default. You can do some really interesting stuff, doing custom calculations and putting in custom normals here to make this node so much more impressive and usable. But for now, let's just put this in here and we have our spirit bomb. Maybe like a full level 5, and then we can make the difference between these two colors like a lot more, so that's a lot more apparent, maybe. Maybe put them into the emissive color. At this point, we can just like play around a little bit. Maybe make this a little bit more like saturated toward green as well. And then just see we want to make this a lower number. It's very counterintuitive, as you see. You want to make this number lower when you want the gradient to be bigger, because math. And just like that, we're creating a little bit of a spirit bomb-like. So there's quite a cool effect that you can use for a lot of stuff. I wanted to cover it just because it's a little bit niche, but it's also a very fun node. Let's talk about distance fields. This is the thing that I've wanted to talk about for a while, because this is one of the last things that we're going to be covering, I think, in this course that is more of a general, you should know that this exists thing. And not a very specific, like, hey, I think that this is a cool node that I just want to cover real quick as part of this. So, distance fields. Every mesh in your game, unless you specifically tell it not to, has a distance field that it emits. And I think we can show it in here somewhere if we look through this. Maybe it is in show, actually. Under show and then visualize. And then we have somewhere in here, I think we have mesh distance fields. This is the thing that we're going to be looking at today. So if we take a quick look at this, you pretty much see that this is the exact same thing, but without the texture applied. But the thing is, we can specifically go into any of our meshes and say that it does not affect distance field lighting, and it's just going to disappear from this, because now it's not emitting a distance field. Everything will emit a distance field by default unless you specifically tell it not to. And how is this useful? Because like distance field lighting, what is that? We're not going to be talking about that right now, but we can use these distance fields in our materials for some quite interesting stuff. So let's set this back to just the normal view. So we're going to go into visualize, and mesh distance fields is going to be turned off, and we'll make a new material here real quick to show off material distance fields. And this one I'm actually going to show you side by side in the viewport, because there's going to be like a lot of stuff that I want to show you going back and forth. So I'm just going to show it to you on one screen. We're going to place a new actor in here, just going to be a simple shape. Let's do a sphere, why not? It'll show the gradients a little bit better. And in here, in our material, which of course we're going to apply to that sphere real quick, we will check our distance to nearest surface. You can give in customized positions here. If not, it's just going to use every single, I think in pixel space, maybe in Vertex, I don't know, one or the other. It's going to take the position of that and check, hey, the nearest surface to a distance field, how far away am I from it? So if we put this into the base color, you're going to see that this thing, first and foremost, just becomes white with some like black spots. And that is because this thing itself is emitting a distance field. So let's fix that first. If we check distance fields, this thing is emitting a distance field, and as such is at all times very close to a distance field. So that's not exactly useful. Whenever you have a material that uses this, the mesh that it's on probably should not be emitting a distance field. So now the entire thing is white because it's more than 1 unit away from a distance field. If I lower this thing to a mesh with a distance field, you can see that there's a little bit of blackness here. And that's not just shadow. If I go into unlit mode, you can still see there's blackness there. And even like down here, it's inside of a distance field. So it's going to render as black. It's not very useful though, is it? Because it's literally just like 1 centimeter, just 1 Unreal unit away from something. It's going to show you, hey, I am now near a distance field. At which point you're almost already clipping into that model. So that's not entirely useful, is it? The thing is, we can just divide this, because this is a number that just goes up and up and up and up infinitely. Of course, the material will only display it up to a value of 1, unless I suppose you plug this into the emissive color, at which point it will start displaying more brightly the further away it is from a distance field. So right now it's really close. If I pull this thing up very far, you can see it starts shining a lot more brightly because it's now further away from a distance field, and now it's a lot closer to a distance field again. So it does actually go beyond a value of 1. but that's still not entirely useful. Unless you want something that is specifically more emissive when it is far away from something, or you can, I guess, 1 minus it and it will be more emissive when it's very close, and then it doesn't matter. What we want to do is we just want to divide this, right? So right now, if we're 10 units away, we get a value of 10. But maybe if we divide this by 100, if we're 10 units away, we're only at a value of 0.1. So maybe even less than that. Maybe we want to divide it by 500. Let's start with that. That means that we have to move at least 500 units away from something before we get a value of 1. And a value of 0 is always going to be fixed at 0, because that's just how division works. So if we put this into the base color, we can now see we have a much more smooth gradient. And I'm going to set this to unlit again to show you a little bit better. You can see the bottom here is a lot darker than the top. And if I move this away, we can see it becomes lighter and lighter and lighter, and it becomes darker and darker and darker. Maybe 500 was a little bit much. Let's actually go with the 100 that I talked about in the beginning there. Now you can see it's a little bit more harsh of a cutoff. And this will just take the nearest distance field that it can apply to. So you can see this works quite well around corners as well. And if I just go to like a totally separate mesh as well, you see that it works quite well here too. And this mesh itself, this is actually quite interesting because this object isn't moving. It's just the shader that's moving it. I think it uses the like physical place of it in the world to calculate its distance fields with not the shader offset. Let me check that real quick. If we go into visualize and we show mesh distance fields, you can suddenly see that, hey, this thing is being moved up and down through its shader. We've talked about that in a couple of videos ago, but the distance field itself doesn't move with that. I'm assuming that's because the distance field is generated on the CPU, and the moving of the world position offset is an entirely like GPU thing. I don't think I mentioned it in that video either, but you probably figured it out if you tried playing around with it a little bit. It also doesn't move the collision, for instance, because that's entirely on the CPU, and shader things happen on the GPU. Now, with all that said, how is this useful? And it can be for certain things sometimes. I'm not going to go too deep into it because I want to show you another distance field related thing. But one thing that this could be useful for is like a force field, right? So in certain cases, maybe you have like instead of having a sphere, we can have like a cube. And that cube is like this big. And nothing in here emits a distance field, but the player will, right? And this will be entirely invisible until the player walks right up to it, at which point that's not the right material. And if nothing around here emits a distance field, I just quickly applied that material, and only the player will, then this will be, for instance, entirely invisible. And when the player gets close to it, it starts showing like the texture of the force field, which could be really quite cool. You can be really creative with this in a number of different ways. I believe like someone I know used this technique to like spawn in objects that emit distance fields along a spline to make like a path appear in a material, something like that. Like you can be really creative with this, but this is just the nearest distance. This is just a one-dimensional bit of information. This is just grayscale. But we have a second node that we can work with. And instead of just the distance to the nearest surface, what we can do is we can get a distance field gradient instead. And this does something quite similar, except that it takes in directionality into account. So if we like apply this real quick, and we don't divide this, and we try to normalize this. If you don't know what normalization does, it takes in a vector and makes it so that the components of it, so the x, y, and z, or the r, g, and b in this case, all add up to a value of 1, which can be very, very useful. So now we can see that we have a bunch of color information here. And this is going to show you, hey, the nearest distance field to me is under me, and I am x amount of distance away from it. But if we move this over here, we can start seeing that the nearest distance field is in that direction, but it's actually in the negative direction, so it's just displaying as black. I was really thrown off there for a moment. If we move it to this direction, we can see it's red. If you want to make sure, by the way, that it works in both directions, like whether or not you're in the positive or the negative direction, you can, after we normalize this, we can make this absolute, meaning that it's just going to take away any like negative values and turn them into positive values. So now that we've done that, you can see there's a lot more like color on that thing as well. So now if we pull this over to this other direction, it still displays as red. And if we pull it over to this side, it will display green. So now we have information regarding how far away from the nearest distance field we are, but also in what direction that distance field is. So, for instance, we can do something like getting our distance field gradient, normalizing it, or maybe not normalizing it, I'll show you the difference in a moment. And then if we multiply that by a number, the shader will actually like try to avoid touching the distance fields, which can be like a really like cool, neat little effect that we can do here. It also like can mess up a little bit, so do be careful with that, but like this could be a neat little effect. If we don't normalize it, that also works well enough. It's just like a lot more subtle. So at that point you have to multiply it just by a bigger number, which does kind of fix the issue that we just had. Also flashing. It does kind of fix the issue that we had a little bit, but you can see it also like blobs down toward it when it gets close and only having one direction. So like this effect probably could use a little bit more work, but you get the basic idea, I'm sure. You can do something similar even without the distance field gradient with directionality. I should point out, you can do something more along these lines where we use the distance to nearest surface. Let's divide that by a number like, I don't know, from 25 or something like that. And then if we saturate this, if we saturate something, we just clamp the value between 0 and 1. And we've gone over the clamp node before, I'm pretty sure. And if we haven't, I assume you know roughly what this does. It just sets any value under what the minimum is to the minimum, any value over the maximum to the maximum. And saturate is just a pre-existing node that takes anything and just clamps it between 0 and 1. So the values are never going to be under 0 or over 1. Then if we get the world space normal here, we can do the pixel normal world space, look at what that does as well, but I want to use the vertex normal for now, because we're going to be offsetting world position, and that's done on vertex basis. So we can multiply that with just a multiply node, and we'll give it a certain strength, like, I don't know, like 20. That might be a little much, to be honest with you, but we're going to figure this out in a moment. And if we multiply those two things together and put that into the world position offset, that will create this like kind of magnetic slimy feel to it. And then instead of what we have now, which is the further away it is to a surface, the stronger the effect will be. We want it actually to be the closer it is to a surface, the stronger the effect will be. So after we saturate this to being a value of 0 to 1, we'll just 1 minus this, which inverts it, and then we'll put that into the multiplication, and now what we have is like this little blobbing effect, which is quite neat. And again, this works quite well around corners as well, and we can do a lot of fun stuff with this. So that's kind of how all this distance field stuff works. You can do a lot of neat stuff with it. Just experiment a little bit with it and try things out. This is one of the last things that I really wanted to show you in like this entire course that I think is pretty fundamental as like one of the tools in your toolkit that you're going to be reusing in different ways and that you just need to be aware of. Which is not to say that this is the end of the material course. We have a couple of videos left to do, but those are more about, hey, I want to show you that these nodes exist because they're just like really, really useful. Alrighty, last time we talked about distance fields. Let's go back to lit mode, just so that we can see all of the beautiful materials that we've made so far. Today we're going to be talking about one specific node that I just want to show off real quick, and that is the texture variation node. Because let's just make a new material real quick, and we'll call this texture variation, something along those lines, and I'll just use a texture sample, and we'll just use the included grass texture that we have on the base color here. So if we just do that and we put that material on here, we're going to at some point see a little bit of tiling. So if we use some texture coordinates here for the UVs, we've gone over all this in previous videos if this is going a little too fast for you. So let's just like tile that by 10 times, and you can start seeing a lot of tiling going on here, which isn't ideal, especially if you're using this for like large open worlds and such. If you're using specifically like grass, you're going to be seeing a lot of it on like a very like big landscape. You're gonna see tiling when you look at it from like above, which is not great. So that's where texture variation comes in, because Unreal, being a game engine, they thought, hey, this is going to be an issue, so let's make a texture variation. And there's a lot of inputs here. We're not really going to care about that. It's going to influence your UVs. So we want to put it in here. So we put in the UVs. Then we can put in like a variation scale, variation levels, like height map influences, masking channels, whether or not we want to like mask on any of these channels. To use dithering, which is, I think I showed that before, which is kind of like fading out in a cheaper way than using opacity. So feathering the patching that it's going to be doing. After all that, you can double click on this, by the way, to see all of the math that it does. It's quite a lot, so we're not going to go over that because, quite frankly, I don't fully understand it, what it does. I know what it does roughly is it takes UVs and at like somewhat random places, it just like rotates and scales things a little bit to create texture variation. Again, it does it on the UVs, so you can just put this into the texture sample, and now if we apply this, we can see that it's a lot less tiling. We still can see a little bit of tiling, and that is where the like variation scale and variation levels come in. So they have default values, but of course we can pull in some values of our own. Let's actually just put this on a cube so we can see it a little bit better. At the moment they're set to 0, so this is just like the default UVs. I think the default for them you can hover over, so that's 3.24 and 6. So if we set this to like 6 and 15, it's going to be a lot more varied, and you can see we don't really have any tiling left over anymore. We're not going to worry about the height map thing, frankly, because I don't think altogether it's entirely worth going into too much. For the most part, you're just going to be doing stuff like this. I do want to show you how to implement these things if you wanted to, though, because the height map takes in a texture 2D object that's not just a texture sample. You can't just put a texture sample into this. This is quite important to understand. If you need to supply a texture to like one of these pre-existing nodes, what you do is you put in a texture object instead, and those you can plug in there, and you can still pick any texture you want. So let's just like go for the noise texture that we have, so like low blurred noise texture, something like that. Anything that you want you can put in there, but it needs to be a texture object which just like puts in the texture directly rather than converting it to RGB data. So you can, what you can't do here is like add some cheap contrast to this, because it's just RGB data. You can't do that coming off of a texture object node, so it's a little bit more limited. Going into a texture object node, you can see we can output like a bunch of different types from the texture that we input. For the most part, we're just going to use color. But again, I don't really care about using the height map here. Just wanted to show you that, hey, if you run into a node that requires a texture input, it's likely going to need a texture object instead. We have a height map influence, which of course is the influence of the height map. If you put one in, we can mask channels. What I want to show you here is the dithering, random rotation and scale, and edge comparison. These are bool values. So we can just make a static bool here, and we can plug those into there. And that'll give us the possibility to say, hey, we want to apply random rotation and scale to this, yes or no. Because just look at over here. Right now, it's applying random rotation and scale, and if we turn that off, there is like the slightest difference. Things aren't being warped as much. Which might be a good thing if the texture you have, you don't want to rotate and scale them, you just want to like scatter them randomly. Use dithering. If we turn that on, the edges become a little bit less obvious. With this texture, actually, it's quite easy to not use dithering. So if you don't have to use dithering, you probably shouldn't, because it does take some extra instructions. Which there's actually probably a good point to talk about that, because there's a short video otherwise. Anyway, down here in your stats, you have base pass shader, the amount of instructions, and then the vertex shader, the instructions. This is how complex your material is to calculate. So if you have like freaking 3,000 instructions in a material, you might have like very good material instancing, you might have like huge custom data to make sure you don't have too many draw calls, all that kind of cool stuff. But then if your material itself has a lot of instructions, that's still going to cost like quite a lot of GPU power. It's always a balancing scale between memory, instructions, and draw calls. So sometimes you want to have like a little bit more instructions to be able to take care of things with less draw calls. Sometimes you're like, maybe a couple more draw calls is fine if it means that I don't have to add like 500 more instructions to my material. That's just something that needed to be mentioned at some point, and I'm definitely not going to be making a separate video on. So there is that. So that's the texture variation now. There's not that much to it. I just wanted to show you, hey, this exists and it is very useful to be able to use. Next time, we're going to be looking at another very useful node that I just want you to know exists, because it's going to save you a lot of headache at some point in your life, I'm sure. And then we'll have finished the entire material course and we can move on to something a little bit more exciting again. For the introductory course of materials, this is going to be the last video. I will keep doing material videos in the future, of course, so if you want to see those, subscribe, like, all that kind of stuff. But today we're finishing off the introductory course, like everything that I think you need to know to get started with materials. You're not going to be a material expert once you've watched all this, but you're going to have a good starting point. And the last thing that I want to talk about is texture projection, because we've been using entirely UV-based texture rendering up until this point. But you can actually project textures in world space onto objects. So if you have an object that doesn't have good UVs, or for any other reason you don't want to use the UV space, you want to project textures onto an object, that is possible. And you can do it from any direction or all directions. So let's take a look at that and make one last material for this course. So what we're going to be doing is we'll call this a material projection. And I will add a world aligned texture node. This takes in a texture object. We talked about that a little bit in the last episode. This is not a texture sample. This is a texture object, quite a little bit different. We're going to just use a texture object here, and we're going to just simply use a noise pattern, tiling noise. There we go. So if we put that into the texture here. Okay, so now we have a bunch of things that have default values. For the most part, you can just leave these alone. It's actually very, very nice. And we have a couple of outputs. A XY output, a Z output, and an XYZ. So this one will align this texture projected from the X and the Y directions. So that is coming from both of the sides. We can also project only from the Z, which will project it just from the top of the world, entirely again in world space, onto any given object. We also can do XYZ, which will just blend everything together. I'm just going to show you by putting these into the base color. And you can even see on this, it's projecting from the side, so the very top of it is getting stretched out. You can even see it more if I turn this into a cube, right? From the sides, it actually projects pretty well. This is not using the UVs at all. It's projecting onto it. The top, it doesn't work quite as well. if I use the Z texture, it will project perfectly from the top, but the sides are like they look a little bit like a barcode. But if I use XYZ, it will pretty well, like sometimes the corners are a little soft, but for the most part it will just project it from all three directions equally pretty well. And since this is being projected in world space, and this is really the cool thing, right? We can apply this to like a object here. Just imagine that this is like a rock material or something like that. If we actually compile the material, it will now display here. And again, since this is in world space, if we move this around, you can see that it's kind of like showing new parts of the material rather than them sticking to the actual object. And that might seem like that's not that useful, but now if I create a second cube and I just put it in a random place, there's no texture seams. The textures are entirely seamless. Well, mostly. The textures are seamless. So if we do this on like a do we have like a rock or something like that, a boulder maybe? Let's do it with spheres instead. We can just select the material, by the way, by browsing to it like this, and then we have it selected so we can apply it to the next thing that we select. So with these spheres, it will be a little bit more obvious if I do this, that we can very easily use this kind of material to like build things that will, especially if we don't have like lighting applied to it, the textures line up fairly well here. So if you have multiple rocks that you're trying to put together to like make a rock formation, a projected material like this could be very, very cool to use. Of course, this is just the texture. We also have a world aligned normal, which is the same thing. We just use a texture object, but we have a normal map instead. And this has an XY texture, XYZ, XYZ flat top, Z texture. You can figure it out pretty easily yourself, I'm sure. And just like with a lot of the other nodes, I don't really feel like it might be all too interesting to be going over all of these separate pins because they're pretty self-explanatory, right? The texture size is the size of the texture. So if we put in like a 111, I don't actually know what the default value is. It's 64 by default. So if we set this to 32 instead, that might be a little bit more reasonable. And we put that in there, it's going to make the texture twice as small. If we set this to 128, it's going to make the texture twice as big. It's pretty self-explanatory. The world position is just the data that it uses for the world position. So that's what makes it world aligned. If for any reason you want to make this like local aligned, you can put in like a local position node, or you can do some creative stuff, some creative math. But now if we do this, for example, we should be able to see if we move this, the texture won't change anymore because it's using the local space, which will just project this without it changing the actual texture on it when you move this around. So if you have an object that needs to be projected onto for whatever reason, but also needs to be able to move around without the texture doing weird stuff, this is kind of what you do for that. This is just a bool, again, for exporting for float, which is honestly something that I've never really looked at and used, so it's probably not that important. This is the world space normal of the object that you're working with, and then we've got some projection, transition, contrast, which is just a scalar value. These two are the only real important pins, I would say. Everything down here, like you can read up on. It's not that important to look at. For the most part, we can just world align texture, texture object, texture size, world position, either X and Y, or Z, or all three. Personally, like I use a world aligned texture for my floors, just like Z projected in my game. Like every floor is going to be the same size as a result of that. Otherwise, getting the UV scales for every single object that has like the floor texture on it to match up with each other so that all the floor tiles always are consistently the same size is actually a nightmare. So just world projecting that from the Z up is a very easy way to make sure, hey, it's always consistent. Again, this was more of a I just want you to know that this exists kind of video to round off the material course with. We're now finished with the material course, so there's going to be like a full upload with all of the parts of it. That's not to say, again, that we're not going to be making any more material-related content going forward. There's a lot of things to talk about, but at this point, I think you have a pretty good start to start looking up more specific how to make X, Y, or Z, instead of just really needing like a basic understanding of how the material system works. And part of that is also because I want to, at some point in the future, maybe it'll be following up this, maybe there will be something in between, I want to make a particle, a Niagara course as well. And particles and materials are inherently very tightly linked together. So I needed to do this first before I could start with particles, because if people don't know how to make materials, I can refer them to this playlist or this full course or whatever. So thanks everybody for watching. We're going to be back with another course. Again, it might be particles, it might be something else. I'm not entirely sure yet. It's been a lot of fun recording this, and I'll see you later. Ha! I lied to you. I said that the last video was going to be the last thing in the material series. We actually have one more thing to do. And that's entirely not due to the fact that I misread my own schedule and I forgot that I had this video planned. That's not it. It's just because I figured I would lie to you. That's just a funny thing. Okay, let's get into this. I want to talk about post-processing, because that is technically a material thing. And while we're not going to get very deep into it, because it could and potentially will be an entire series in and of itself in the future, I want to show off kind of what you can do with it, what it is. I real quick covered it in my Unreal Basics playlist, but that's more so hey, this thing exists and you can color grade with it. So let's, in place actors here, add a post-processing volume. And as long as your camera is inside of this volume, let's scale it up like quite a bit here. Whatever you set this processing volume to do will affect the rendering of your camera. So for the most part, we can do things like adding bloom, changing the exposure, changing some of the color grading stuff. So we can say, hey, as long as we're in here, we want the temperature to be a lot like warmer. So now, as long as we're in here, everything is going to feel a little orange, and then when we exit out, it's normal again, and so on and so forth. We've probably covered this, you've probably seen this before, I don't really care about it. One other thing is we can set this to being boundless or infinite extent, unbound, and now it will just always affect the entire world. So even though we're outside it now, if I go and change the tint, it will become more green or magenta, even though we're outside it. So that's kind of a cool thing you can do. We're not going to be talking about all of the color grading stuff here today. I could make an entire mini-series on that as well, especially since this is actually related to what I do in day-to-day life, which is video editing. I do a lot of like color correction stuff with that as well, so that's quite fun. But what we want to do today is we want to look for the post-processing materials that we apply to this, because we're going to write our own post-processing effect as materials and we can apply that. So if we just add one thing to the array here, we can choose it's going to be an asset reference, and then we can put in pretty much any material that we want. For the most part, these aren't going to do anything because they're not set up as post-processing materials. Let me show you a couple of examples of post-processing materials that I've made in other projects, and then we'll get back to this and I'll just show you a couple of things. So right here we are inside of my own game project, and this has a post-processing material for like a line shader on it. So if you look at this, if we just look at it in game view, you can see like a lot of things have these outlines around them. Like this platform over here is a very good example, but also the enemies are good examples. These coffins over here, you can see it a little bit on this skull, and that is all done through a post-processing effect. So you can see if I look up my post-processing volume and I turn it off, a lot of things suddenly look a lot more flat because it is not rendering all of those lines. And especially things like these bricks on the wall and the tiles on the floor, if you look at them, they start looking a lot less detailed because they don't have that contrasting little edge to them. So in this one we have that very same line shader. Actually, it's a little bit different in this one. I continued to develop it in my current game. This is just a messing about game that I never actually really got that far into. So that's where this line shader originates. Then in my current game I added a couple more things to it, like taking distance into account a little more. But we also have a cell shading effect here. So if you look at the mannequin here, you can see that the line shader is definitely like unperfect in this case. But you can see that he's like not entirely smoothly lit. Matter of fact, he looks a lot like what he does in unlit mode, but it's just like a little bit different still, because there's still lighting being applied here, as you can see right over here, but it's in a more cel-shaded kind of look. A look that I didn't use for my current game because it didn't really fit as well, in my opinion, but still quite a nice little thing. Also, this project is so broken. I started in Unreal like 4.25, and right now it's at 5.3. So yeah, it's kind of broken. And if I then open up that post-processing volume, I actually also have a pixelation filter here. So I can turn that up to pixelate my viewport. So now everything looks a little bit more like pixel art. And this is how you can make a game entirely with like 3D assets, but in the end have it look like a 2D game. You're going to have to be careful with it to make it actually look good, but it's entirely a possibility that you can do. And there's so much more interesting stuff that you can do with post-processing effects. So let's go back to our tutorial project and I'll just show you about a little bit. So in here, let's make a post-processing material. We'll just put a new material and we'll call this material PP for post-processing. Just very quickly, just gonna show it off to you. In the material domain, we're gonna go into post-process. There's a couple more things that I could maybe cover in the future, but I don't really think that I want to cover it right now. There's things like lighting functions, volume lighting, and user interface. If I ever do like a lighting course, that makes a lot more sense for lighting functions. Same with user interface. I don't really see myself covering that in the future because I'm by no means like good at making UI. But post-processing could also be an entire series in and of itself, which again, it might be in the future because I really like playing with this kind of stuff. We only have a emissive output color, and most of the post-processing workflow relies on a thing called a scene texture. So we have the scene texture color. This will supply us with simple color and size and in-size pins, and we have a scene texture ID drop-down menu, and there's a lot of these. So some of these won't work very well for post-processing. We can also use this in normal materials as well, this node. Not really what we're talking about at the moment though. Because what we can use is post-process input 0, 1, 2, 3, 4, 5, and 6. And this is, if you hover over it, it says this is the first post-processing pass. So if we just hook that up, that's literally just your scene texture. As in, this is the image that the engine simply outputs to your viewport once it's done rendering your scene. And usually this is the only one that you will use. You can do some stuff with this and then send it through to post-process input 1 and then do some more stuff with that. But you can also just like do that more stuff directly inside this material with it. So it's usually the only one that you use, but that's why there's 6 of them, so that you can use them on top of each other. I guess technically speaking, you can then send it off to another material to do something with. Never really done that, but it is something that you can do. So post-process input 0, again, is just the thing that the camera renders. And now, if you want to add something like cheap contrast, just like a contrast thing through post-processing, when we add that, you can see it becomes a black and white image because cheap contrast only works on the grayscale. So what you want to do is we want to then multiply that by the original again, so that this is now the luma values. We'll multiply that with the color values, and that will just give us the same image, but slightly more contrasty. So if we put in a value here, the contrast to 0, this is going to make it do nothing. If we set the contrast to 1, it's very contrasty. If we set it to like 0.1, it's a little less contrasty. And so on and so forth. You can do some neat stuff with this, like 1 minus it, and that'll probably like be a real wacky effect. This inverts the contrast, so now all of the shadows are going to be raised up, and all the highlights are going to be crushed down. So you kind of get like a negative exposure. All the colors are going to stay the same, but you have a negative exposure instead. Speaking about which, you can also do a negative on the colors themselves, which will also then do a negative on the exposure. So we can 1 minus the outputs directly and put that into the emissive color, and that will just make a negative of whatever we have. But now you can see the exposure is also getting flipped, not just the color channels. So if we want to have all of the colors being flipped but have the exposure remain the same, what we do is we just invert the colors, add a little bit of contrast, invert that exposure, and then multiply that together. So both are negative, so the exposure is going to be positive. Now, again, it's a little iffy to wrap your head around, maybe. Again, it's a lot of math, but the end result will be something like this. So all of the colors are now turned into the opposite color. So reds are now blues, greens are now like yellows, orange, something like that. Just the opposite side of the color wheel, but the exposures remain the same. I can show you a little bit easier if we put it in here. So we have the material for post-processing. When we apply that, it takes a moment to calculate. Do make sure that you press apply here to compile it. So now you can see all the exposure remains the same, but the colors are the other way around. So again, these used to be, that's my other project. These used to be purple, now they're green. That's the opposite of green on the color wheel. It's purple, of course. They go back and forth between like green and yellow now, I guess. So this is a much more pleasant version of turning something into a negative image because it's still using the proper exposure. So that's quite a fun thing to do. But we can do much more with the post-processing as well than that, because we have a couple of things here. So we have, for instance, only the base color. We can just output the base color of whatever we're working with. So now, even though we're in lit mode, we're only seeing the base color of everything. And this is actually the way that my cell shading works in that project that I just showed you. Because what it does, real quick rundown, is it uses the base color and then it multiplies that with a cheap contrast version of the actual output, and then it like clamps things so that you get this like banding. You have like 3 or 4 different shades that things can be, and we simply just use the base color and then like base color multiplied by, I don't know, like 1.4, and then another one with like base color multiplied by 2, and so on and so forth. So that's how you can make a decent cell shader. What else do we have? We can just like display the metallic value of everything in our scene. And as you can see, now we just got an output of only the metallic value of the entire scene. So if you, for instance, want to apply certain effects only to things that are metallic for whatever reason, you can very much do that. Same thing with the roughness, material ambient occlusion. You pretty much have access to render passes for all of these separate layers of information. We can even show the normals with the world normal. So now it will show you all of the normals in world space of everything, which makes also for a very like weird looking effect. If you have like a game where you have, for instance, a character on certain substances and you have like a retro inspired game, for instance, I think that this could be a little bit of a neat effect. I probably would add a like absolute node to this as well, so that it doesn't make half of them black. And now we have like a much more like, this feels like you've been using substances and it's like 1992 or something, right? So a lot of fun stuff that we can do with that. So if we take this scene depth, for instance, this is also one that I really, really like doing. We want to divide that by a number, and that creates this kind of foggy effect. Because what this is doing is it is giving you a number between 0 and infinity of how far away any given pixel on your screen is from the camera. So when we are very close up to something, it's going to be rendered as black, but the further away it is going to get rendered as something closer and closer to white. And once it reaches a value of 1, it will be fully white. And the value of 1 in this case will be 2,000 units away. If we set this to like 7,000, then a value of 1 won't be until something is 7,000 units away. So the gradient will be a lot more smooth and subtle. And for instance, this is the thing that is used to make that line shader. What you're doing is you're comparing every pixel on your screen to the pixel next to it. And if the scene depth is significantly different, that means that there is a distance between those objects, meaning that they're separate parts of an object or separate objects altogether. So we render a black pixel on that edge. That's the basic idea. I have an entire video showing you how to set that up as well. But now let's saturate this so that it's clamped between 0 and 1. And then we can 1 minus this, and we can multiply this with, for instance, the actual just post-processing input 0. And if we put that into the emissive color, we now have this like fog effect where things fade out into a fog without actually there needing to be a fog. There's also just straight up a node that does something like this, but what we could do instead is maybe instead of doing that, we can hook this up into, and let's set this back to 2000 just to make the effect a little bit stronger. We can maybe input this into the contrast, right? So instead of doing it right the way in there, and then we can just hook up the 1 minus thing directly into the contrast node here. And now we should see if we get closer to this, the contrast is a lot less, but the further away we get, the more contrast we're going to apply, or the other way around. I think it's the other way around actually. Like the further away we get, the less contrast we might have. So maybe we don't want to do that. So yeah, now the further away we are, the more contrast we're going to get. So if we get very close to something, it's going to look more or less normal for the most part. And then we get further away, and that creates more contrast. So let's set this back to 8,000 to make that gradient more gradual again. And we can do some like wacky stuff with this. This is effectively how you create a depth of field effect that is entirely custom. So instead, let's do something like this, and I'm just showing you examples here in a somewhat random way, but we'll have a normal scene texture and then a desaturated scene texture, and we're going to loop between the two of them. So we have our scene depth as the alpha, then we have the A input being the scene texture, the B input being the desaturated scene texture, and that will go into the emissive color. And now you can see the things close to us are in black and white, and the things far away are in color. I probably actually want that the other way around. So let's get rid of the 1 minus in this whole equation. And this is actually a bad example because this object itself is grayscale. But now, again, we can see that this is in color, but the further away we get, the background is entirely in black and white. And if we go very far away, we can see slowly all those things turning black and white as well. So have at it, do a lot of fun stuff. Again, this is kind of a chaotic video of me just going like, oh, you can do this, and oh, you can do that, and so on and so on and so on. I really like playing with post-processing effects because as much as I like being creative with normal materials, this is really where I feel like my creativity is being like tickled in all the right places. Specifically with the scene depth node. As you could probably tell, I really, really love using this node for different things. So again, we're probably going to do a post-processing series at some point in the future. It's not going to be like a 15-part series like this one was. It's going to be a little bit shorter, but we'll play around a little bit with some of the things in a more structured and less chaotic way than we did in this video, because I'm entirely aware that this is very chaotic, and that is just what we're gonna have to deal with. I suppose you can see this as a bonus video, because I told you that the series was over, and then it wasn't, but now it really is. So next time, we're gonna be doing something else. Whether it be the post-processing, the particles, or something else entirely, I'm not entirely sure yet. I'm sure we'll figure it out. And a very big thank you to all of my Patreons. You can see them on screen right now. If you want to help out supporting the channel, there's a link down below in the description to the Patreon page. A huge thank you to my Cave Student tier supporters, Earl Monteval Erno, and my Cave Digger tier supporters, Sir J. Thomas,